Hi, folks, and welcome to another edition of Regulator Geeks. What I've done here is inserted a little introduction to the recording of that session that evening, because in the weeks since we met, I've had some second thoughts about some of the criticisms I've leveled at the second stages we evaluated. Specifically, some of the graphs we show of performance, while valid at the surface, don't account for case geometry in the water. Since the diaphragm hangs just a little bit lower than the exhaust valve in the water, that preloads the valve, probably improves cracking effort, but more importantly, it subtly attempts to open the valve and assist breathing at depth. And what I don't know is the effect at great depth. We tried to extrapolate from surface measurements to depth by using total molecules of gas, i.e. high flow, and tried to equate that to lower flows at depth. And while some of that is true, I think some of the criticisms I leveled at the second stages was invalid. So take what you see tonight with a grain of salt, and take a look at the comments I'm inserting at the end of this tape, especially those of you that are sort of seeing this for the second time since you were there that evening. Take a look at the comments I make at the end, where I try and relate some of the things that I've thought about after talking with the ScubaPro engineers to performance at depth, because I think the S270 and S620 Ti were actually better than I gave them credit for. One, because of their incredible stability, and two, because of the effects of case geometry and preloading the regulator valve. This is I'm always learning when we do this, and I think the next test will be to take my rebreather down to depth where I have an unlimited supply of gas, and then use 5 or 6 regulators on a couple of stage bottles to see what it's like at 130 feet with thick gas and hot tuned regulators to see if they do cross over into free flow. And that may change some of my enthusiasm about the G250 if in fact they do that based on case geometry. So more to follow, just won't be this time. Again, thanks for joining us on Regulator Geeks.
Well, I think we've got a critical mass here. Let's rock and roll. We'll be covering a lot of ground tonight, and as always, I want you to jump in and ask questions, interrupt anytime through the chit chat. Please use your space bar to unmute yourself so we don't have extraneous noise capture the screen for those of you that are monitoring Zoom. For those that want to, you can just full screen this view, and I will pull in the gallery from time to time if we have participants to capture that screen or use that screen to show the mobile camera. The big question tonight is do I really need that new gear? She thinks you do, and part of the driver for that has been the regular introduction by ScubaPro of newer and better, which occasionally means more expensive, but I think we have a little surprise tonight in that regard. ScubaPro has a long and storied history that goes back 50 plus years, long before they were even ScubaPro, and their penchant for design excellence is pretty unsurpassed. They have a lot of haters, obviously, because of being the 800-pound gorilla and being somewhat unapproachable with regard to questions from divers or participating in DEMA or some of the other measures by which people judge a company besides the quality of their gear. They are expensive, but you can never fault the quality of their engineering. as I suggested at the outset, we've got way too much to cover in an hour and a half, and that's all right. It'll just give us a reason to come back for the next edition. But this is some of the stuff we're going to cover. As always, when you decide to jump in on these seminars, I force you through some theory as well as playing with the toys, just because that's my philosophy, that there are too many regulator technicians out there that are just parts changers. The more we know about the theory, the better we can make the judgments that we want to make tonight, like which one's the best, which one's the one for me. So let's jump right in. If we look at, where's my slide? If we look at the construct of a balanced valve, and I should say from the outset that we're talking balanced valves tonight. We'll leave the downstream discussion for another day, because tuning those regs is wholly different from a balanced reg. I once again want to thank Bob Kuvalon from ScubaBoard for the loan of this tremendous cutaway barrel. And that too is where we'll be limiting our discussion tonight. This is a balanced barrel regulator discussion, and we'll leave center balancing and the D series and the pilot and the Air One and a couple of variants on that for another evening. But it's kind of amazing that we can breathe through a 4 millimeter hole, 4.5 millimeters. But with a driving pressure of 135 psi, we do. And one of the striking things is how little it takes the valve to open for us to get a breath. If I force you through the physics of it, it actually makes sense. Because if our valve orifice is 4.5 millimeters, we need to open the valve enough to at least to let that amount of area for gas flow on the other side. And interestingly enough, the other side of the orifice is larger. It's larger by about 0.5 millimeter, which plays an important role when you do the math. If you look up in the right-hand corner there, we've got an area of whatever it is, 15 millimeters square in a 4.5 millimeter orifice. With a larger knife edge, you now have to lift that knife edge X millimeters with a circumference of 5 millimeters to come up with the same area. And that maximum lift, as we can see both in the math and in the live demo, is just a hair over a millimeter. We'll tune this barrel tonight for those that are interested, just to re-emphasize just how simple it is to tune a balanced barrel regulator, and yet it's also surprising how often that gets screwed up. The valve is a simple toilet seat valve lifted by a lever, and Scubapro has gone through a lot of iterations of their lever over the decades. This is the one that started it all, the lever that actually goes in this 108. This 108 is the only unbalanced reg here tonight and has a heavy spring inside, but was noteworthy for it being diver adjustable. You can adjust the spring tension and therefore the cracking effort once the knife edge was set. And the more the spring tension, the harder it was to press down the lever. But like all simple devices, it's a function of mechanical advantage. And the Achilles heel for this was the difference between it and its successor. Here are two more levers. Actually, let's go back to big. Here are two more levers that followed in short succession, because as they discovered, the lever opening was not sufficient, or I'm sorry, the seat opening was not sufficient for the same shape lever, because of the size of the foot, this foot is quite narrow, and the next iteration had a larger foot, which, although it decreased the mechanical advantage, increased the amount of flexion as the lever fell and increased valve opening. When ScubaPro went to the S-wing poppet, that little toy right here, we'll take a look at in a moment. The S-wing poppet required a slightly different engagement, and they went to what's commonly called now the curly foot lever. And the curly foot lever has almost, not quite as much, but almost the same lever height as the second version. But of more importance, it was taller. And we will look at that in a variety of regulators tonight, because that affects valve opening just as much as the mechanical advantage of the length versus the foot. That then proceeded from there to the next iteration, which is what we see in the flagship regulator now, the S270 or the S620 Ti. And it's just a different shape, but if you measure the height of this and the angle, it's exactly the same. It has a different profile, but the lever tops are about the same place as this third generation lever. The barrels that started the adjustable craze are all dependent on the knob assembly that fits in the end. And let's see where we are here. This is the schematic for the cutaway diagram for the 620 Ti, and you can see quite quickly how much, I guess we'll turn it so it matches the picture there, how much higher the profile is on the lever for the S620 Ti compared with the 109, with the balanced adjustable, with the G220, and we'll see that as we open it up. At much taller lift augments what we saw in the last slide, which is the throw of the lever, which is significant when you have a tall profile. The sacrifice you make when you have a lever as tall as this is that its base of action is relatively narrow, so the initial force to open the lever is higher than it is with a low flat lever. And the way ScubaPro got around that is by changing the coefficient of friction with the materials that they used to create the lever, decreasing the surface area compared with the flat top we see here, and then choosing the plastics that fit on the back of the diaphragm for optimum slipperiness. But one of the things that we'll end up spending a lot of time on is the choice of knob, if you will. The problem with most of these designs, that's not what I wanted. Problem with most of these designs really relates to how the knob action is handled. And if you go back as far as the old G200, the G200 started out as a unbalanced regulator with a downstream poppet like this, but then was converted, like the 109 was, to a balanced version. So this is essentially the plastic edition of the 109. This then became the 250, but it initially started with a non-diver adjustable knob. This was set by the technician, and you got what you got. For most of us, that is a non-issue, because I don't know too many of us that will mess with the lever in the water, with a few exceptions. A lot of what you need to do can be controlled by the Venturi lever and not by the cracking effort. And we can have a whole argument about whether changing the cracking effort changes your air consumption. But the noteworthy piece of all of this is the tiny, tiny orifice that these regs started with for the flow of breathing gas. And the 108 was a noteworthy exception. Look at that huge oval in the 108 compared with what followed in the G250. And that has eventually gone full circle so that now in the 620 we have this large square orifice for gas flow. But the problems of barrel regulators persist. The fact is that once you've opened your lever seat, and let's go back to the slide that shows that, the gas has to follow a fairly circuitous path out of the hose, past the orifice, around the seat, down along the poppet, and then in this case through the spring. And for those of you that were here for the last little chit chat, we talked about the downstream C350, which pulled that spring and put it down here behind the poppet, giving a fast and free pathway for airflow. So how companies have wrestled with this has been a challenge, and part of the advantage of the titanium barrel of the flagship S620 is that it can be so thin for the same strength. And by making it thin with a predetermined outer wall size, you have much more room for gas flow inside the barrel. And it's going to be subtle things like that that are going to markedly affect how we see performance change as gas flow increases. I think it's fair to say that we can make any regulator breathe adequately all the way from this piece of junk Aqualung ABS to the 620 and everything in between, as long as gas flow is low enough. And when we talk about work of breathing, it's more than just cracking effort, although that's the primary determinant of how easy it is to get things started. If your technician has tuned the spring too tightly and you have to suck hard to get that lever down, you're going to dislike it from the very beginning. But there's a lot more that follows after that with regard to work of breathing. And the work of breathing slide up in the corner of your screen puts the numbers behind that. This is a picture from Pete Wolfinger's book, Regulator Savvy. And it's an old work of breathing curve. I've seen this curve so many times in one production or another. It's obviously not copyrighted anymore, and I don't know what regulator it came from, but this is a pig of a regulator. Surprisingly enough, though, the work of breathing for this regulator came out at only 1.2 joules. Now, I don't know what that means. It's really hard for me to put joules into a useful frame or useful format. Thinking as a diver, we all think of cracking effort. So if you parse this graph, you can see that there is a millibar scale on the left, and if you translate millibars to inches of water column, which is how we commonly think of cracking effort, 15 millibars, that dotted line there, is essentially 15 centimeters of water. And so if you see where that regulator first opened and where its worst inhalation effort was, it was somewhere around 3 inches water column. And for those of you that tune your own reg, it'd be nice to have a cracking effort of 1.2, 1.4 on the high side, with an octopus running maybe 1.4 to 1.7. So seeing this regulator peak at 3 inches is a little disappointing. But as I say, this is an old curve. And some other factors combined to make the total work of breathing for this regulator only 1.2 joules, which is pretty respectable, and it's actually within the CE norm that was used a couple of decades ago. And that all revolves around Venturi augmentation of flow. And that's going to occupy most of our time on the theory side tonight, talking about what Venturi does to improve work of breathing. If we look at most modern regulators, we expect to see, and this is very idealized, we expect to see a work of breathing loop that's more like the green and orange circle or oval, with green being the inhalation side and the orange being the exhalation side. Much smaller total work of breathing. And the work of breathing, just for comparison, with that 1.2 you just saw of the S620 Ti is about 0.57 joules. Unbelievably low. And we'll touch on how they've gotten there, because this is, in many ways, a machine-driven metric. Having a manufacturer able to claim these wonderful numbers has to do a lot more with things that we don't pay attention to as we take a breath. This work of breathing loop, and I'm not going to bore you with this much longer. I apologize if it's too much theory, but this is a little bit closer to current times. It's still 15 years old, but this is a reg where it dropped the work of breathing from 1.2 down to 1.1 joules, an old Ziegel regulator. And what's worth talking about here is what goes into the test. This is done at 170 feet for Scubapro, 198 feet for the Navy. This one was done at 198 feet. But when the Navy does this at the experimental dive unit, it's 198 feet and 4 degrees centigrade. And so this is done at a relatively balmy 51 degrees, where freezing wasn't a concern. And what has driven the EN 250 certification that you see stamped on every plastic regulator body now is a function of not only the standard 62 liters a minute of diver breathing rate, but a low temperature, because the adiabatic cooling of that gas coming through the orifice and expanding automatically creates an ice ball. And how well a regulator sheds that is a primary determinant of a regulator's ability to get the EN 250 rating. There is a new EN rating or CE rating that you'll want to pay attention to, though, because it implies some design changes that are good for you anyway, and that's EN 250A. And what they simply did was they took these conditions, 198 feet or 170 feet, I actually can't remember which it is, and 62 liters a minute. They then doubled it by adding a second diver. And if they could have 2 divers breathing a reg that way, still come up with less than something like 1.2 joules, and do it at 198 feet, you acquire an EN 250A rating. The ability to handle that much airflow is what makes it something worth looking for when you choose a regulator. Even though it was designed around a cold standard, the notion of essentially having 125 liters a minute implies that when you get down to 90 feet or 120 feet and you now have to struggle against the current and you have to really work that, you know that your regulator isn't going to increase its cracking effort, isn't going to make you work for that breath on top of the situation that you find yourself in with thick air at depth. Last bit of theory here before we sort of jump into what this means in real terms. You'll notice in the last slide that the test was conducted at 2.3, or if you have 2 divers, 4.6 cubic feet a minute. Well, that's an average consumption of air. And remember that that's only measured during the inhalation half of the cycle, because the exhalation half of the cycle doesn't give you any credit back. And then when you look at the inhalation half of the cycle, um, the typical breath starts out in a sine wave fashion. And the inhalation half of the sine wave starts slow, accelerates, and then decelerates as you get ready to exhale. So while the flow is only 4.6 cubic feet a minute for 2 divers, if you look at the steepest part of the curve, that may triple. And that is the direct lead in. If we look at needing 8 cubic feet a minute instead of 2.3 cubic feet a minute, if we need 8 cubic feet a minute, if you have to have a regulator that can handle that much flow, or 2 divers with that much flow, now we're seeing some substantial airflow. Because when you take a quiet breath, a slow breath, if you're breathing 10, 12 breaths a minute, your air consumption, as you know from trying to measure it and decrease your SAC, is going to be less than 1 cubic foot a minute. The good guys are down around 0.5, and the braggarts are down around 0.2, 0.3, if you believe them. That's a long way from 8 cubic feet a minute. And yet regulator performance really revolves around that. Now, that's all measured with the MagnaHelic. And I thought I'd do a little demo here just to put this in real terms. So here I am, or here I will be in a moment with a MagnaHelic. And we're just going to take a breath. Now what I've done with this MagnaHelic, oh, I'm sorry, I didn't change the slide here. What I've done is I've moved the 0 on this MagnaHelic because I want to not only see inhalation effort, I want to see exhalation effort at the same time. And the proper MagnaHelic to use for that would be a -2, 0, +2, and I just don't happen to have one for this single test. It's not something I use in my shop work, although behind me there's a -5, 0, +5 that we will see as part of our regulator testing. But we'll just use this with the 0 moved so you can see. Typically when you test a regulator, you'll attach a mouthpiece, a tube, and then this just sort of taps off the side as you suck through it. But this isn't going to be suitable for the demo because it's got this little tiny orifice, and I'm going to breathe hard, and that'll change the results. So let's just do a quiet breath. But I'm going to tuck this in the side of my mouth as sort of a sensor for the pressure or vacuum that's formed as I breathe in and out. So if I'm breathing quietly, if I'm noodling along in the water, I would love to have a regulator that delivers at 0.3 inches of suck and an exhaust valve that allows 0.3 inches of exhalation effort. There just aren't any. The D400 can be tuned to 0.6. The double hose regulators can run 0.5, but they're so dependent on regulator position behind your back that that 0.5 cracking effort is only seen in one position in the water. So that's cheating a little bit. But we can't get what we want. You can't get effortless breathing, at least in a natural feeling way. What you do want is not to have to suck, not to have to work to get your air, especially when it's thick air at depth. And so manufacturers take a number of techniques to get around that. One is the volume of delivery that they can provide before cracking effort becomes, or before inhalation resistance, I should say. Cracking effort is just the static measurement when the valve opens at that moment. But the dynamic inhalation resistance is a measure of how much of a sensation you have to work that regulator to breathe. So delivery is one phenomenon. There is another regulator, though, that uses an entirely different technique, and that would be the Poseidon. Poseidon is a provider of air par excellence, but it has a very different breathing pattern. It has a somewhat higher cracking effort, around 1.4, 1.6, so you have to trigger it. Then when you do, it fills you up. And so this is very popular for deep divers, and that particular second stage is rated to 600 feet. Um, but those aren't what we're talking about today. We're talking about our standard barrel reg. So let's see what reg has to be able to provide when you're working hard. We've learned to accept 1.2 inches to open the valve when we're diving. We don't find that like breathing through a straw. It's okay. So even though it's not normal, it's satisfactory for us. What's it like when I'm working really hard? When I don't want any more effort imposed upon when I'm breathing? I'm going to hyperventilate just a little bit and let you watch the needle. You'll see that my suck pops up about 1.5 inches. Exhalation doesn't drive it out quite as far, although that may have been a function of how I turned the sensor in my mouth. But you can see when I was really working hard, albeit not very fast, but at least taking up deep and rapid breath, I sucked at about 1.5 inches. So we should choose that 1.5 inches as a marker for where we what we don't want to exceed when when we when we dive. Pete Wolfinger is the author of Regulator Savvy. Regulator Savvy is the Bible for regulator geeks, and it's worth every penny of the $30 or $40 that it costs after mailing from Scuba Tools to be able to read about regulator mechanics and theory more detail than we can ever cover in an evening. The piece that applies tonight is what he calls atmospheric inhalation resistance, AIR. The AIR line for this regulator, see, is going to go someplace after you open the valve. Cracking effort for this regulator is set for this diagram at about 1.6 inches, pretty high, but it's for purposes of argument, that's fine, doesn't matter. The point is that airflow from the regulator can go one of two ways. If you turn the air off and you suck hard, it'll immediately go up to infinity because you're sucking as hard as you can. Well, it won't. It'll go as high as you can suck. If a regulator performs adequately but poorly, the more breathing you try to do, the more resistance you will see in the circuit coming through that valve. If, on the other hand, the regulator is able to provide everything you need, you'll have a nice flat line. And that's a good standard to think about, being stable over any range of gas flows. And then to the extent that the regulator uses the Venturi principle to open its own valve wider, you'll see an increase in airflow. And that will make it easier and easier to breathe, which is a good thing, especially out on the right-hand side of the curve, where you're moving lots of air, you're working hard at the surface. Or theoretically, if you're doing modest work but at depth. Out here, we've got 12 cubic feet of surface molecules passing through the regulator. This is the Venturi that's been provided to make inhalation effort near zero. Well, at 30 feet, you've got twice as many air molecules. And as a rough approximation, if you look at half the way down that line, in other words, the resistance at 6 cubic feet a minute of breathing, the equivalent at 30 feet will be like 12 cubic feet because you have twice as many air molecules passing by. And that's actually a theoretical consideration that I've asked a number of people about. I'm still working on it. I had a talk with Rene Dupre of ScubaBoard, of Scubapro for about a half an hour just this afternoon, trying to work on getting ScubaPro to help provide us the correlation between something that we measure at the surface like this and the fancy work of breathing loop that we see at 198 feet. Because I have no way of measuring flow at 198 feet the way the Anstey machine does. But that's $40,000 that I don't have to spare. In any case, we're going to use this principle tonight to evaluate the regulators apart from our visual inspection. As I suggested, stability is really a key for these regulators, and the ideal curve would be one in blue, where the regulator opens at, let's call it a super ideal 1 inch of cracking effort. That's really lower than most regulators will tolerate for other reasons. But then once that valve is open, the effort the inhalation resistance drops because of Venturi provision of extra gas flow. So the ideal regulator would drop as soon as the valve opens, and the harder you worked, it would drop down to almost zero effort using the physical principle of Venturi induced negative pressure to provide you as much air as that regulator can provide, all the way up to 16, 20, 30 cubic feet a minute, which at the surface is meaningless, but at 6 atmospheres, down at your max recreational depth, would be the equivalent of, say, 8 cubic feet a minute. Um, Down at 150 feet would be the equivalent of 20 or 30 cubic feet a minute at the surface, at least in terms of molecules. What we don't know are the Reynolds numbers and the density effects, whether or not that's true. But I'm still going to try and pry an answer out of an engineer, maybe from Scuba Labs. Well, this is the ideal. A regulator that drops low makes it easier on you, even if you're working hard, and stays that way, come what may. The more typical regulator is just stable. It stays where you want it. It's engineered to provide exactly the flow that you're asking for without accelerating that. And that's an engineering design change, because it's relatively easy to bump it down closer to the zero line, which would be truly no effort of breathing at all. But the problem is that at that point, the valve gets a little unstable. And if you don't have something to control that slope, that negative slope, once you get out here, at some point the reg is going to turn and start blowing at you. Free flow in with each breath. It'll stutter. It'll do any of a number of things that are physically uncomfortable. So the typical reg, as I say, cruises along at ISO, whatever that is, 1.2, 1.4 inches of water column. And then when you get out here to the nether regions, when things are really flowing hard, then engineers aren't able to control it quite as well. And so you'll see a range of performance, either the reg that will stay stable right out to the limit of what I measure, or one that'll start to see enough turbulence come in that the reg begins to fight you a little bit. See your effort of breathing increase. So before we start opening up regulators, I'm going to show you one short video. I think it's about 1.5 minutes long, and it's one that I did on the bench behind me. I've gone through a lot of air in preparation for this little evening's deal. I've gone through about 250 cubic feet of air measuring these regulators, but it's been interesting. So what you're going to see is 1.5 minutes, which is really a slow motion movie of about 20 seconds of measurement, because any longer than that and I'll empty the tank. So I need to do it fairly quickly when I measure it, and then I slow it down so that you can see what's happening. What you'll see is airflow going through this rotameter. There is a regulator attached, mouthpiece up on the bottom. It's resting in a little basin of water to stabilize the diaphragm, because as you know on your own, when you suck on a dry reg, it'll honk at you because the diaphragm is flapping in the breeze. There's no surface tension of the ocean water holding it in place, and so it honks at you. So the regulator is resting in a basin of water, which slightly lowers the cracking effort, but I've already measured that separately, and keeps it from fluttering. Then I use a vacuum source to increase the pull through this, is pretending to be a human on the top of this tube, sucking as hard as I can. In this case, the vacuum source will suck all the way up to about 15 to 18 cubic feet a minute. I can't measure it past 15, but I know I can go higher because I can hear the machine whining. And we'll see what the regulator does. A bad regulator will just climb right up, go from 1.4 to 2 to 3 to 5. And Aqualung had a limit of 6 inches water column at 15 cubic feet. And that's, in fact, what this ABS performs at. It hits 5.5 inches at 15 cubic feet. So it theoretically is within Aqualung standard. But as I say, it's a piece of junk. This is okay for a class out of air drill or a shallow water air drill where panic isn't a phenomenon. But if you need to donate air, or if you need to put this in your mouth, having primarily donated at 100 feet, this wouldn't be my choice. Conversely, a poorly adjusted regulator will drift down towards zero and then cross over into free flow. And we're going to look right now over 2 minutes at two brief clips of that. The first one is a standard regulator test. As you can see, at about 4 to 6 cubic feet a minute, this reg is holding right where it started, around 1 to 1.4 inches of cracking effort. And the nice part about this, since this is an atomic regulator that I photographed, is its incredible stability. Whether it's 4 cubic feet, 6 cubic feet, 8 cubic feet a minute, that inhalation resistance doesn't change at all. Well, oops, it does. I was doing this test, and you can't see it in the gauge down at the lower right. That Dwyer gauge is just too dim, although I did turn the light on, but it's calling about 130 psi. The dynamic intermediate pressure went from 135 to 130, sucking that much gas, but the reg is keeping up. And you can see it there. It started to drift from 1.4 down to 1. So I said, okay, this reg is heading towards zero, doing great performance. But then all of a sudden, the needle started to jump. Went back up to 1.5. And then it kept climbing 1.6. And I said, what's going on here? This is an atomic reg. This is a $400 second stage. Why am I seeing this? This is terrible performance. And then it got even worse. It hit 2. I said, I'm not used to seeing this, until I just happened to glance down at the IP gauge. And the IP gauge, if you can see it, is reading 122. And then it's reading 118. And then it's reading 110. I can see it on my monitor, even if you can't. And what has happened here, it's now down to 110, 100. I'm doing a test and I forgot to pay attention. The tank is almost out of air. I got about 300 psi left in the tank. This is this regulator's performance at 68 intermediate pressure. In other words, if your tank was so low you could only generate an IP of 68, now it's 50, you could still get a breath, even though you'd be sucking at 4 inches of suck. So that was just really tremendous performance, but it turned out to be an odd explanation for something I didn't expect to see. My IP was only 50 at the end of the test, and as we saw, the reg had to work extra hard to generate that. So that's a climb off the top of the charts, either poor performance in the regulator because there's so much turbulence inside the case, or as we saw in this case, inadequate first stage performance, as might have been seen with an unbalanced first stage near the end of a tank, where IP is, or unbalanced piston, where IP falls off towards the end. So that was a fortuitous accident. The second video is one that I'll want to show you a slide first. If we look at a graph a la Wolfinger of the performance of a regulator. This is an actual pair of tests that I did on an Apex TX100. And the first one in the solid line was when I just sort of took it off of the pile in the back, hooked it up, and ran the test. And I'm not a big fan of Apex, even though ScubaBoard has a huge fan base for it. I think their performance is not as good as some other manufacturers, and this is a fair example of why. We have a rig that was actually set to pretty hot, tuning at 1.0 inches cracking effort, and usually when the valve opens, we see a drop, like we have on this dotted line. But this one immediately took a jump to 1.2, and as soon as I got up to 2 cubic feet a minute, it was 1.6. By the time I got to 4, it was over 2 into what I call this little yellow zone, which is even above Aqualung standard. This regulator was not performing well, and I ran the test anyway. And you can see that with really hard work on this regulator, there was just a lot of resistance created. And I thought about this and thought about it because I, even as much as I am mezzo about Apex regs, the TX100 is a good reg with a big lever, a big case. It should have done better than that. Well, I took it apart and looked at it, and it was just corroded uh, beyond belief. It was a reg that I'd never serviced. I just sort of had it in the class pile. And even though I was able to make it crack at 1 inch of a cracking effort, its barrel was just full of verdigris corrosion. The lever was very sticky. And so I said, okay, let's see what Apex can really do. So when I cleaned it up, to my surprise, I didn't get much more than an early bump of drop like most regs do. You open the valve and get that first burst of flow, but inner turbulence immediately created the same amount of resistance inside the case, uh, and is part of why I'm not an Apex fan. But what it then started to do, as you really started to pull air through that regulator, its case geometry then began to shine, and you can see the difference between its dirty and its clean version as airflow increased. Well, as I kept increasing it, it kept having greater and greater Venturi effect. And what I want to show you is the tail end of this curve, when you can see the regulator shift from suck to blow. In some regulators, it's quite abrupt. It'll go 0.20, bam, +1, +2. It'll just flip over into free flow. This one was a little bit more gentle, a little bit more controlled, but it's one of the few demonstrations of crossover that I have for you because most regulators stay above 0. So here's our 1-minute video of that. So once again, as we hit 12 cubic feet a minute, this rig is really easy to breathe. If we could get every regulator to sit at 0.2 to 0.4 throughout the breathing cycle, that'd be great. By the time I got to 14, this rig was ready to kick over. And so even though my scale won't show it after we hit 15, I drove the vacuum source even higher. And if we had the sound up, you could hear it. You could hear it working. As I pushed my vacuum generator to the max, probably up around 18 or so, this reg actually went into a positive flow of about 2 inches. It was really really blowing hard, and you can see in the video there the IP, the dynamic IP of this Mark 11 diaphragm is still 127. So as even though it was putting out 20 cubic feet a minute, the regulator, the first stage, was keeping up, and that's pretty cool. All right, enough of the theory. Let's have a little fun. Let's look at these toys and see uh, where we started seeing the design changes that made a difference. Okay, if we start with the 109 and balanced adjustable, um, these cases were handmade. The engineers at Scubapro at the time, whether they got lucky or just wanted a pretty case that seemed to mold itself around the mouthpiece and the barrel, they got it right. Um, and the problem was that because these were hand brazed, and you can see the little ridge in there where the mouth tube protrudes through. Some mouth tubes protrude through a lot, some just kiss the edge of the case. So they all had slightly different turbulence pathways inside. There was no deliberate attempt to make use of the Venturi effect, although I'm sure it was known to the engineers at the time. It wasn't a deliberate attempt. So both the 108 in the downstream version with this heavy spring and unbalanced poppet is exactly the same case as the 109 that followed it. What happened is after that, though, is they converted from an unbalanced poppet to a balanced one. Now, Kuv has an example. Is Kuv here yet tonight? I don't see it. Oh, yeah, he is there. Kuv's got an even earlier version of this poppet, but the key to it is that the poppet has a hole in the middle. And that means you have intermediate pressure coming through the orifice, traveling all the way down the stem, and collecting in this little balance chamber on the end. Of course, there's a spring in the middle. This spring is much lighter than the one 108. But this spring is lighter because now the air pressure inside this balance chamber pushes the poppet closed. It helps keep the poppet closed against the orifice, keeping the reg sealed. Now, if IP drops for some reason, i.e. if you had an unbalanced first stage, as we had so many of in the old days, as IP dropped, the pushing pressure behind the poppet inside the balance chamber would also drop, and it would be easier for the reg to open. So normally, where a downstream reg has that constant spring that keeps the valve closed, it gets harder and harder and harder to breathe as IP drops, just as we saw in that one video snippet. Balance regulator would actually do okay because spring pressure would not be augmented by as much um, pneumatic pressure, and you could still open the valve relatively easily. That's why in that video snippet we saw that it only took 5 inches to open that reg despite an IP of 50 at the end. So this was the first one, single O-ring. It was followed in short order by a single piece assembly that you didn't have to assemble. This has an extra O-ring up inside. It has a molded seat that is permanently bonded to this plastic poppet. So replacing it was a more costly issue for the company. And instead, by going to this this one piece poppet, all you had to then provide in the service kit is this tiny little top hat seat that fits in the hole in the end. And that's your service right there. As I say, Kuv has one that's even predates this that you could reuse because it made use of the same sort of flat seat as we had here. This is just a little disc of rubber. You can punch this out yourself out of Viton, EPDM, or even plain old butyl rubber with a is it 9/32 punch, and bingo, you've got a new seat for 6 cents. As I say, the top hat seat's a little more expensive, it's $4 a piece, but it still was cheaper for the manufacturers than providing a whole new top end. The next advancement that was made on that, though, was the move to the S-wing poppet, and the classic S-wing poppet has persisted for decades ever since. One, you can see the cutouts in it. It's very thin molded because remember, all of your gas has to flow around the corner and down alongside this poppet. This heavy piece of molding was a big impediment to airflow that was improved with the S-wing poppet. Additionally, the S-wing poppet added a wiper O-ring to the top. One of the risks with this sort of arrangement is that the sealing O-ring is down inside that little groove, and that's a place for grit to collect. You collect a grain of sand in there, and now you've got a valve that won't open. By adding this wiper ring 1/8 of an inch higher, now that wiper ring is always within the 1/8 to a 1/16 of an inch of the top. Cleaning this out every time the poppet moves, dislodging any debris and protecting this against failure. So we were stuck with this case and its handmade constraints all the way through the balanced adjustable. The balanced adjustable for the first time addressed an issue that will come back to us in the future, and that's the exhalation work of breathing. It had this little tiny exhaust valve in its first models, just like the original 108, but the very last editions, I don't have one, they're relatively rare, had a larger exhaust valve of the same size as the G250 that followed. So it markedly improved performance on the exhalation side, and the S-wing poppet improved performance on the inhalation side. But then when the 250 was introduced, everything began to change, because with molded plastics, you could now have a case configuration inside of just about any shape that you wanted. And so what they did was they tried to mimic the 109 as much as possible, but they also added a new uh, component. And this was called the Viva, the Venturi. The Kuv, help me here. What's Viva stand for? Um, vacuum induced vacuum. Something is Venturi assist. Can't remember. But in any case, it made use of the principle of
Yes, Venturi assist.
Thank you.
My video is not working, Rob, or I'd show a picture of that gray poppet that you were referring to, but I can't seem to get my camera on. That's good.
Well, if it works later, just go ahead and jump on in and show us, because it'll be interesting to see the progression. In any case, the Viva valve, as it was called, took airflow right out of the barrel. There's our same hole that we have here, same barrel, relatively small hole, and it took it and it directed it at that vein. And the technician would adjust the angle of the vein to do one of two things. Either let it bounce against the bottom of the vein, as this one would, and shoot out the mouthpiece, or obstruct the flow as it came out of the hole and create turbulence. And so you would either have a lot of vacuum assist or no vacuum assist. And as I say, this was a technician adjusted angle between max and min, and the instruction to the technician was to change the angle so that when you bang on the purge lever and the reg went into free flow in the shop, it would self correct in about 3 seconds. What would happen is air would start jetting out of the mouthpiece. There'd be so much airflow inside the case that the increasing airflow would create a degree of turbulence. And what you wanted to do is increase that turbulence just enough that after 3 seconds or less, the free flow would stop. And that was what Scubapro recommended for optimum adjustment. That has since been replaced, and this is a more modern Venturi valve, by a pre-dive switch. We have dumbed down our understanding of regulator performance so that now it's just an on-off switch. You don't want your reg to free flow when you jump off the boat, you turn it to pre-dive, and you want it to perform, you turn it to dive, and that's all there is to it. And unfortunately, there's a lot more subtleties to that are lost with today's crop of rapidly trained divers. In any case, case configuration now became important. What is Scubapro going to do next? They hadn't yet thought of changing the contours in the case. We didn't have CAD CAM design back in 1978 or 80, or at least if they did, it was fairly primitive. And so they hadn't yet begun to model airflow within the case, but they did understand Venturi principles. So they had the Viva valve. The next that they wanted to look at, though, was what they could do to improve diver resistance. Here's the deal. When you've got this G250 valve, actually, let's clear out the deck just a little bit, make it easier to understand. When you've got that that adjustment knob, you have a couple of critical things going on. We look at this regulator, you can see that the foot of the lever is pinned between the white of the poppet on one side and this square broach on the other. So the backside of this square broach pins the foot of the lever on this side, and the poppet pins it on that side. So the lever has to sit upright, or does it? And here's the problem. You can see that this lever has a little flicker to it. Why? It's certainly pinned against the poppet, but what's happened is the orifice has been screwed in to the point that the broach is no longer holding the foot on this side. There's a little slop in there. The more you screw in that orifice, the more the lever will drop. Let's demonstrate that. If we take our lever adjustment tool, and we're going to screw in the orifice in the back, and I'm going to do it without regard for cutting the seat, because this is just a demo. And this is sitting sideways, so I'm going to turn this vertical so gravity helps me. When I screw this in, look at that lever drop. Look at the flop in there. When I screw it out, the lever rises back up again. With it in, you can see how much the orifice has driven the seat forward. It's still pinned on one edge by the poppet, but the top half is loose. And the problem is that if you have to have your regulator lever at that height to seal, in other words, if you have to screw in the orifice that much, that tightly to seal, then this is all you're going to get for valve opening. Just that little 3/8 of an inch. And when we go back to Cove's demo reg, you can see that 3/8 of an inch of throw is going to open that valve 1/3 of a millimeter. We need a whole millimeter. We need 1.01 millimeters to get the full benefit of that hole. So lever height is the single most important error that do-it-yourself technicians and shop technicians make when they adjust a rig. They put it together, they have it all set up, they put it on their air supply, and it leaks. When it leaks, they add a little movement to the orifice. Leaks, they add a little movement to the orifice. Leaks, they add a little movement to the orifice. They hand it back to the diver. Well, it's a little stiff, but it's working. And this diver takes this rig down to 80 feet or 100 feet and dies, because that's as far as he can open that valve with thick air. He hasn't got enough to survive on. Lever height is critical, and is not emphasized enough in manuals, because they've got these lever height setting tools, but they don't explain why that's important. So that was part of what drove the shift from a low profile lever to an arching lever that would sit much higher in the case. As you saw in that one little slide, the problem is that it takes a low friction deal to get that throw initiated, but it's still improved safety. Once you've got a seal, let's assume that you've got it right there at optimum lever height. You had your seal and your lever has no wiggle in it at all. It's just perfect. What determines cracking effort? When you want to move that poppet away, when you want to open the valve to breathe by pressing down on the lever, what resists that? Well, what resists it is the spring behind it. And this is what brings us to the adjustment knob. The adjustment knob is fixed in the G250. Let's drop out the retaining pin. It's a fixed knob. So if I take this barrel apart, there's my adjustment. My adjustment sits against the balance chamber that's hiding inside. And in fact, if I were to push on that, the lever pops right back up again. And that's the same thing that the knob does. But the knob has a single position. It sits right here. Why does it sit right here? Because that's where that little hole is that locks the pin. That pin hits the base of this threaded area, and you can't unscrew it any more than that. So when you put these together, you always have to put it together enough that that hole is clear so you can get your pin back in. That's just a minor point. The bigger issue is that when you screw it out, that's as far out as you can go. So if you screw it out as far as this goes and you still have a stiff regulator, you have no way of backing that spring out anymore. Conversely, if you have a weak spring and you have a really low cracking effort and you try and screw this knob in, put more tension on the spring, bingo, you get the cracking effort you need. But now you don't have much room left to further increase it if you want to put this reg in pre-dive or in a stiffer position for an octo. You can't get to the top end anymore. So the engineers of Scubapro began working on the knob question. And what happened was pretty much a disaster. The G250 became the G500. And this is a G500 barrel. And what they've done is really smart. It's really inventive. What they did was make a replaceable outer knob that's sealed with an O-ring against the inside. And what they did inside this knob is instead of having a fixed assembly, they have a further adjustable micro screw inside. So now, if you unscrew this, it moves that way, it puts extra pressure on the spring and raises cracking effort. If when you assemble things you can't get it low enough, you screw it the other way, which takes the pressure off the spring and gives you the low end cracking effort that you want without moving the orifice. In other words, it was a huge safety advance. Now you didn't have to drive that orifice in to tighten up the spring and therefore cause a lever drop. You were able to keep your lever at maximum height, and now you just shifted the base of the pressure plate on the spring, something that the old knob couldn't do. Oh, I'll screw it back in already because it was a fixed piece of metal. Now you have an adjustable one. Well, why was this a disaster? The disaster was they have this beautiful sealed assembly, and when they put it inside the cap, there was no way to tune it because with the cap off, the assembly was loose inside. It was sealed, but as soon as you pressurized the regulator, it would blow out the end. So you'd put it together, put the cap in, test it, take the cap off, twist that thing, pressurize it, blow out. Oh, you remember you got to put the cap back on. And this went on and on and on until they invented an adjuster, an external adjuster. Their original one was just like this. I mean, they didn't discover this after the fact. They marketed this regulator with the need for the technician to buy this toy, this little metal piece on the end. It had a part number, and the shops all had to buy one, and that enabled you to seal it and tune the reg without the cap on. Scuba Tools then came out with one that had a floating adjustment so that you could do it without removing the tool, and it was a slight improvement on it. But for the most part, it was a pain in the ass, and this didn't get a lot of love from the technicians. But here's a really cool thing that we ought to look at anyway, because it was something that they have since given up, and fixed in a different way. Let's see if I can get that. Here's a cross section on the left of the G500 knobs. And here's the really cool thing about it. If you look at the left-hand side of the bottom picture, this is the barrel assembly under action. You've got air flowing down the middle of the poppet. There is no balance chamber with a little cap on the end, like the one I showed you here. There is no balance chamber like that. It's that whole assembly, that whole knob assembly instead. So with a hole in that balance chamber, the air flowed all the way through the assembly and then collected underneath the cap. So it doesn't matter how it balanced. The point was it formed the pressure that enabled you to have a light spring. But here's the neat part about it. When you turn the regulator off, when you turn the first stage off, and the pressure inside this assembly dropped, the spring would push the balance chamber assembly up into the cap. And it took almost all of the pressure off of the seat. And this is what they called their anti-set feature, preventing your top hat seat from acquiring that ring that causes all downstream rigs to free flow 3 months after you tune them, because they develop a groove that's the same as unscrewing the knob. So this anti-set feature was really, really inventive. And unfortunately, it was ahead of its time, because it came with the mandate that you not take the cap off in order to test the reg unless you had that special tool there. So the do-it-yourselfer certainly couldn't do it. And so when they finally fixed it, and this knob assembly that you see on the right persists to this day. An equivalent to this is actually what's in the S620 Ti. And they gave up the anti-set feature. They gave it up in exchange for being able to work on the reg without a fancy tool. If you take this screw out on the right, you have direct access to the micro adjuster inside. And the micro adjuster is sealed by these three these three O-rings inside the case. And its micro adjuster itself is sealed inside the barrel of it, so that when you take out the screw, the reg doesn't leak. And you can adjust it just with a simple tiny screwdriver on the fly. It takes no more than that to tune your reg on the fly. Then you just screw the knob back on and go. But the downside of that was that now you don't have an anti-set feature anymore. And that's why, for example, the S620 comes with its own anti-set button. It pushes down on the purge knob and locks in place to hold the knife edge away from the seat instead of the seat pulling back from the knife edge as the 500 did, and is a throwback to 1969 when the old 109 had its own anti-set knob. In fact, it was the key, the Scubapro key, and you stuck it in the middle of the S, turned it, and that pushed in on the diaphragm, lifted the knife edge off the seat, and your seat would last twice as long. Before that reappeared in the G250 HP, another disaster. We went through the whole 250 period, where the seat would just age prematurely because it was constantly under pressure from the spring. So that was a magical improvement, going from no micro adjust to a micro adjust. Now, should you go and buy a G260, which would be the current day version of a regulator with a micro adjust, or should you buy an S260 Ti again to have that micro adjust, as opposed to something really simple that I'll show you at the end of the evening, but that doesn't have it. If you're a tinkerer and you want to have your regs in tune, it's very nice to be able to just pop this cap off with your fingernail, stick a screwdriver in there, and retune your reg, and you can do it with a bowl of water. That way you can keep it always in the sweet spot. Because what happens when you take your reg to the shop? They tune it at whatever cracking effort you want, or they tune it to what Scubapro says, which would be 1.1 to 1.4 inches. Or if they don't want you coming back complaining, they'll tune it to the high end of that so that you have a good firm pressure of the knife edge. And then you struggle along with it for the first 3 months until the seat takes a set and it essentially backs itself off a little bit. And now you get the 1.1 that you wanted when you walked in the door. If you ask them for 1.1, they'll give it to you. They may try and talk you out of it because they know that 90 days from now, that groove that you've created in the seat will now cause a little slight hiss. How do you fix that as a diver? Well, you just dive with the cracking knob turned in a little bit. That may fix it, it may not. It may require an orifice adjustment. Just a hair of a turn. They'd rather not have that complaint or that misunderstanding, and so they'll tune your reg stiff. But the micro adjust makes that easy to keep on top of, and that way you can use your knob the way you normally would and not have to slowly work it in to make up for the groove that's going into the seat. Does it really matter though? No, it doesn't matter. It's no more than adding a 1/12 of a turn, 5 minutes on the clock, to the orifice when your seat takes a set and the reg begins to hiss. But what you have to remember, having said that, is that if you're going to put on your do-it-yourself hat and say, okay, I can fix this, I can fix that leak. There's a little leak from the seat having taken a set from that sharp knife edge. I'm going to fix it. I'm just going to screw it in. Well, what we're talking about is 5 minutes on the clock. That's it. It's not a quarter of a turn. Quarter of a turn, and you've just condemned yourself to inadequate performance at depth. And this is why you have to be aware of the guy at the beach who wants to help save your leaking reg. He says, oh, I can fix that. And he comes along and honks in a half a turn. Leak is gone, but your lever is only half as high as it was before, and you're asking for trouble. So, as I say, does the micro adjust matter? Not really until you get to the end of life of that regulator. And there's the problem that you have. When you have a really weak spring, the only way to make up for it is to just to drive that spring in. You've lost a lot of capability. Conversely, if you happen to have a stiff spring, and there are some steels that will stiffen up instead of get weak, your minimum cracking effort may climb, and you can't back it out anymore. And if you had a micro adjust, you could pull off another one. You could use that without changing the spring for another decade. In today's, buy a new regulator for $125. It's a little hard to justify a piece of equipment that you want to last for your whole lifetime, but I think from a theoretical standpoint, it's worth doing. All right, let's see where we go from here. We've talked about the knobs. We've talked about the improvement in the micro adjust, and we'll open up one of the G2 or the S260 knobs to take a look at that. The next thing we need to look at, though, is the evolution in the cases and the diaphragms. You have already seen the lever change. We showed you the S270 with its tall, high-profile lever with a huge throw, and a huge throw means good valve opening. But in order to do that, you can't do it with an old G250 diaphragm. The G250 came with a diaphragm like this, and And the problem with it is that it's extremely low profile. It doesn't have a lot of excursion. It certainly is enough to do what the lever is capable of, but it has to be adjusted perfectly. You have to set it in the case so that its lever is at perfect height, because if you've lost part of the height on the lever that's as flat as this, you've already lost 25% of the total excursion, and performance will suffer. With a much taller lever, that uh, constraint goes away. And so what they've done with the G260 is they've given you a diaphragm profile. Let's see if I can show it better. Diaphragm profile is much higher. So you can preserve that throw even with some technician missteps or do-it-yourselfer missteps by letting that lever drop a little bit. It won't carry the near lethal consequences it does in the G250. So diaphragm height was one, lever configuration was another, and that brings us next to case configuration. Now that you've got a molded plastic, you can do lots of things. You can do whatever you want with the mold to create the sort of airflow that your computer decides you need. And that's really what I thought ScubaPro did, is they modeled this all out. And that wasn't only until this year that I discovered that that's not really what ScubaPro does. Yeah, they use CAD CAM, but they mostly do it to create the model, the picture of how it's going to look after the fact. The way they do this is iterative. They will carve it just like the Ford models carve a torus out of clay and run smoky air over it to see how the airflow travels. It's not all computer modeled. It's done the old-fashioned way, and the computers just make that easier. But if you look at these two cases, you'll see an important subtle thing. See if I can get the light right for this. I guess it's going to be looking at the 10 o'clock portion of both cases. Right here, you see a relatively square step leading to the Viva vein. What's happened in the G260 is they've rounded that off so that now air going out the mouthpiece doesn't go around the corner. If you compare the mouthpiece sizes, look how much bigger the G260 is than the 250. This is big changes for little tiny effects. And again, this is ANSTI machine driven. And you can't feel it as a normal diver unless you're going to hit 150 feet and be working hard, and then run across a subtle feeling that made you say, "Ah, oh, there was something not right." There, you might be able to feel the effects of the more turbulent airflow in your 250 and the less turbulent airflow in your 260. It's hard to say, but there were some other changes that were important besides the shoulders of the mouthpiece tube, although that was a big one. They did simple things like going from 6 spokes to 4 spokes in the exhalation valve. In other words, get things out of the way of the airflow pathway. Because what has happened as the decades have gone by is they've done as much as they can do on the inhalation side. This barrel looks no different than it does on a G250. Well, it does. The orifice is a little bit bigger, and on the plastic ones, it's even bigger still, but it really is no different. They're working under a constraint that doesn't change. What else has this enabled them to do? Well, this reg is a left-hand, right-hand reg. You can pull this barrel out and flip it the other way, and take this deflector and remount it in a different position, because there's another breathing hole on this side of the barrel that's covered up. So that not only do you have air coming out of that side of the barrel that you just see in the light, there's one here that's covered up if you want to turn this into a left-sided regulator. Finally, the exhalation pathway has been significantly altered. Instead of being a simple flat space, again, where air has to go around a corner and then out the valve, it's been turned into a chute that directs airflow. And that's because the emphasis now to improve your ANSTI numbers, to give you bragging rights in the magazines. You can't do any better on the inhalation side, so the only thing left to do is exhalation. So they're working with bigger exhaust valves. They're working on smoothing the inside of the case. And then finally, we bring ourselves to the last new deal. The G260 has changed the exhaust T. Now, this actually, I don't know where it was introduced first, whether it was on the G series or on the S series that we'll get to next. But what we've got here essentially is a, a Viva for exhaust, if you will. It's not really Venturi assisted, but it's suction assisted. What this is a chimney. It's got a vertical component to it, and when they started making these, they made the flare really big. Divers wanted the bubbles away from their face, so happy to comply, and they ran this way out to the side, and they had to be nice and big so that they wouldn't create a resistance pathway of their own. And what happens here is that as the air comes out, you see this area is a little higher in the water, at least in the normal diving position, than this area. And so the bubbles want to come out. They suck the bubbles that are behind them, and they help facilitate exhaled airflow. It's very subtle because you got to say, this isn't going to improve my bubble flow past my face very well, but it certainly changes the numbers of exhalation resistance. That allows them to have a squashed ANSTI loop, a squashed work of breathing loop, and a lower total work of breathing. Can you tell as a diver? I doubt it. We never mind having to breathe hard on the way out. We have the muscles for that. It's the inhalation muscles that are troublesome. But in any case, this is a deliberate change on their part. They have used this in the G series and the S series, both, and in the C series. There are downstream regs that then went to balanced regs to improve that total work of breathing loop. What's happened along the way, though? Well, what they've done is they've gone back to the original Viva vane that they had in the 250. A nice, dumb, straight vane that improves flow, and it's this position for diving, and it's in that position for pre-diving. And that's all you get, and that's all we're going to tell you, diver. Turn it on, turn it off. Well, that's a step back in time, because if you go back one generation, and this isn't on the 260, but this is on one of the S-series regs, back when the G250 HP was introduced, they also introduced a Venturi vane with a cutout in it. And this is when they were really thinking. If you oriented it this way with the remember now how that works. I always forget. I always have to go back to the manual to figure out which is the rental version and which is the other. Who can tell me?
Facing toward the diaphragm is rental. Facing toward the mouthpiece is for me and you.
Bingo. Bingo. There it is. This is from the G250 HP manual. So this is now going back 30 years or so. And there was a rental position and there was a maximum performance position. Here's the disappointing part about it all. If you look at the service manuals for the last regulators that have a scalloped Viva vane, the way they teach you to put it back together, and they don't have these paragraphs in anymore, is to put it in with minimum Viva, with the crescent facing the mouthpiece. No, they don't ever give you the option of switching the other way to have the crescent facing the diaphragm for maximum performance. They've dumbed it down until they've lost it, and finally in the last version of the 260, they just took the option away altogether. And to me, that was a disappointment. There is some interchangeability. I want to remember which regulators you can, but it's not with this one. This Viva vane is too short to put a scallop vane into the 260. But they don't test it this way. So this is lost art kind of stuff. But if you have an early S600, and we'll talk about that um, next. Here's an early S600, and it has a scalloped vane. And if you want this rig to be able to do its best, you need to reorient this. You need to pop this out, turn it over 180 degrees so that the notch is facing the diaphragm instead of the mouthpiece. Because otherwise, you're in the rental configuration, the non-free flow configuration, the stupid diver configuration. And if you want to be able to give yourself the best performance, you'll flip it around. Now, what that also means is that it'll be more susceptible to free flow if you bang on the purge. And it means you need to think back 2 or 3 decades. And you may want to dive this, especially if you're diving deep, with the Viva vane turned back just a few degrees, just a little bit past the dive or before the dive position, to decrease some of that susceptibility to free flow that they tried to engineer out by turning the vane around altogether. But that'll give you the best performance, the lowest work of breathing at depth when you need it. Well, that's the trigger for us to move to the new configuration, because they talked about diaphragms giving a nice tall diaphragm for a long throw for maximum lever opening. They talked about changing the exhaust valve. They've lightened up the valve as much as they can, engineering wise, but they still were left with this huge case. And divers wanted smaller, lighter, easier to drag around. And the problem is an engineering one. If you make a smaller case, how do you keep the same lever without the lever tips being over here off center? And they engineered that one out by tucking that as far into the knob area as into the nut area as they could. They decreased friction, but they couldn't change the constraints of case dynamics because of the smaller area for a negative pressure to develop and create that Venturi suction that holds the diaphragm down and keeps the valve open. So when you look at the flow diagrams that we'll look at in a minute, you'll see a change in performance. Nonetheless, they still went through the same iterations on the case, carving the shoulders away here to improve airflow, increasing the size of the mouthpiece. And they've even done something really imaginative with the C series, which has become its own balanced regulator now. This C series that I have is actually the downstream version, the C350. But if you look at the C370, this 370 is a standard barrel just like this one with a small case. And I think it was a marketing decision. We're going to try and go either way and see what the divers love. And the problem is that the S260 has just too big a following. But the C370 has some magical stuff going on. You talk about friction. Oh my goodness, they have an offset lever. They don't have this double-footed lever. So friction in this sucker is really low. And because it's almost a circle, they can have a long lever because here's the point of contact at the top point, but it migrates inward as it drops, and it migrates inward as it drops, and it migrates inward as it drops, so that they can retain contact in the center of the diaphragm disc much longer than they can with this short contact surface with the straight tips. This particular hinge is very low friction. So in the balanced version of this, you have really tremendous flows. Why do you have tremendous flows? Well, the case is subtly different. I don't know if we can see it. We'll look at it right this way. If we look at this one from the side, look at the elevation of the mouthpiece there. What they essentially did is they carved out a whole roof for gas flow, because when you compare these two, the problem with the offset lever is that you now had to move the barrel up in the case to get the diaphragm, to get the lever in the middle of the diaphragm. This one has the barrel right in the middle of the case, easy pathway to the mouthpiece. But the C370 has the barrel up high. So what they had to do is they had to carve a ramp for the there it is, carve a ramp for the air to go out and get out to the diver. Um, and they also came up with a huge, absolutely huge outflow tract. If you look right there inside the reg, um, that square, that set of vertical lines is a gate. Let's see if I can get this gate to open and close. If you can see it, there it's closed. I'm opening it, and now it's just a huge outflow tract from the barrel. They did lose the one thing that made the downstream version so magical, and that's putting the spring out of the way. With their equivalent to the S series, you've got the spring still in the way of the airflow path, and that's too bad. This performs actually better than their 370, but they won't admit it. But in any case, we now have the battle of the configurations, the big case versus the little case, and they've maintained the flow path size here because they don't need those shoulders anymore. What they did have to do, though, was shorten the barrel. And that turned out not to be a problem for the plastic barrels that it was for the metal ones, because they could slide the mechanism over the outside. And why don't we now take us to that last piece of the action and look at that knob assembly in the S600. So now we can see what they did for their barrel assembly here. Okay, so there's the little C-clip that holds the barrel in. Now we'll just push the whole assembly out. Well, this ought to look familiar to you now. It's exactly what we saw with the S500, except that they've changed from that poor knob to the other one. They've gone from a metal orifice to their Delrin orifice, and that's always been an interesting discussion, is which is better for sealing and ice shedding. We'll talk about that in a second. So here's our knob assembly for the latest iteration. The S270 is really no different than that. You have to pry off this decal, which is a sacrificial decal. So as I suggested before, when we looked at that cross-sectional diagram, the knob assembly, once it's out of the way, doesn't affect the performance of this because this is sealed. Once you've got the knob off, it's a simple matter of putting your screwdriver right inside there, and you can adjust the micro adjust inside. The micro adjust itself is removed by screwing the knob in clockwise until you drive it out the front. There's your micro adjust assembly here. It's got this little nipple that this is about the standard position for it, sticking out 1 to 2 millimeters. That means you can back off the pressure on the balance chamber about 2 millimeters on the side, or you can drive in as far as you want. But the threaded screw that's inside it is very tiny and serves no more function than to serve as a contact point for the balance chamber. But it's all sealed, easy to work on for the technician at the one cost of not having an anti-set feature. The move to a plastic barrel was associated with a change from round to oval to square, trying to get more and more flow out of there. But interestingly enough, they found that when they moved to this square configuration, free flow became such a problem but they had to introduce some turbulence. That's why you'll see that most of these square orifices have a little tooth in the middle. What that does is it disrupts flow just enough to create a little turbulence in the case to decrease free flow. That was introduced after the rig was first designed in its earliest models, and they had to put that tooth back in to get rid of unwanted free flow. That brings us to the S620 Ti. This is the 600. What has changed? Well, if we look at the S620 Ti, it's exactly the same as the 600 in terms of diameter, or is it? The case has actually shrunk about a 1/16 of an inch. This is not the same case. You can't use an S600 case on the 620. So they've made it even smaller. They've made it lighter. They've made the purge button very flexible. It's this skeleton apparatus now, which is, let me clear some of the stuff out of the way so you can see. Just move the pieces that we need to keep. So the purge button is very soft and supple. They've introduced something that wasn't present in the 600. The 600 just has a diaphragm and a thrust washer faceplate, so you don't accidentally twist the diaphragm's position. What they've done is introduced something that's seen more commonly in the D series, and this is a cross-flow preventative item for scootering in current. If you turn your face sideways, you have air coming through the front of the case. It doesn't depress the diaphragm and open the valve inadvertently. It introduces a little turbulence in there. It stabilizes the diaphragm. So that becomes, instead of the thrust washer, we have a thrust washer and a cage to protect the diaphragm. Diaphragm is even higher than the diaphragm in the 600. It's really, really high. But otherwise, the lever is almost the same as before. I think there's one slight iteration more, but it's a very minor change. What's the most significant thing about the 620 Ti? How did they make up for the case being smaller? How did they get away with making the case even smaller? Well, as it turns out, because titanium is so strong and so thin, look at the size of this barrel. This barrel is a fraction of the size of the plastic one, and thus has improved airflow internally that makes up for the fact that the diameter of the case is smaller inside. So titanium actually turned out to be a good move for them in this regard. They were able to improve the performance dynamics over the slightly larger case 600 model by adding the titanium. It's not just a bling factor. It's not just a corrosion factor. It's actually a performance factor. Otherwise, the case looks pretty much the same inside as the 600. What they've done is they've smoothed out the shoulders there at the mouthpiece even more, just a little bit. And they've raised the outflow track here, maybe a millimeter. You can see it more from the inside than you can from the outside. Just very subtle. Had better lighting. But other than that, it's unchanged. Poppet is still the S-wing poppet that has been around forever. I think. Did they change the poppet? Kuv, you remember? I can't remember. They may have a new poppet. I'll have to look at the schematic. I don't think so. And of course, they've got.
Sorry, Rob. I'm not familiar with those newfangled regulators.
But well, see, it's got some bling in it though, Kuv. It's not chrome, but it's titanium. It's shiny. It's shiny. That auto attracts you.
Even better.
It doesn't have very many moving. But they kept the straight, flat Viva valve because we don't want to have to think about it. And so let's look at the numbers. When we started, we showed the rotameter and the flow meter, a la Pete Wolfinger, and I suggested to you that I went through a lot of gas in preparing for this, and let me show you why. Anyway, all right, picking back up. as I suggested to you, did a lot of testing in the last couple of weeks preparing for this. This gobbledygook that you're looking at, I'm going to try and make sense of for you. It's one thing to look at case configuration, say, oh, okay, I like that. That's a good idea. Or to look at a small case and say, okay, that's lighter, it's smaller. I like that as an idea. And the next question will be, well, how does it perform? And if you go into the shop, the salesman will tell you, wow, works just fine, works just fine. And for 90% of divers, he's absolutely right. Um, because what are we talking about? We're talking about 0 to 2.3 cubic feet a minute as you breathe in and breathe out at 30 to 80 feet, lollygagging along. And if that's your diving and you never have an emergency, then pick any rig you want. I mean, this is not like the days of the brazed cases of the 108 and 109 where you might have a goofy case that just doesn't breathe quite right. These molds don't change. Well, I mean, they do change. Actually, you can only run about 50,000 imprints through a mold before the mold is degraded because of all the fiberglass inside the plastic. It chews away at the mold and you will have a shape change, and they need to expensively replace them well before 50,000 imprints. But for the most part, these rigs are repeatable from one point to the other. And so if you are a garden variety vacation diver, you're operating, if we look at this slide here, in this part of the curve, 0 to 2, 3 cubic feet a minute. And they're all the same. I mean, you're just not stressing the equipment enough to matter. But the day you decide to take an adventure and you get your deep water certification or your specialty dive or your advanced open water, or you go to Mexico with none of the above and they take you down to 125 feet in a current anyway, you may suddenly find yourself needing the performance out here at the 6 or 8 foot level. If you're a technical diver, even with helium, you may find yourself needing the performance out here at the 12 cubic foot a minute. And the day you are joined by an out of air diver at depth, hyperventilating away, who wants your gas, you hand him your reg, may start to think about that. So since you've decided to participate in a Regulator Geek forum, we'll talk about this part of the curve. How do we make sense of these lines? Well, let's start at the very beginning. In yellow, there is the 109. There is the first iteration, which sort of established Scubapro as engineering geniuses. You had a reg that was tuned to 1.4, and the valve opens and it gets really easy to breathe. But even when things started flowing like crazy through the case, it never climbed over 2 inches of inhalation effort. And you saw me huffing and puffing. I was huffing and puffing at 1.5 with a wide open airway. So if you have a piece of equipment that can give you 2, that's not much extra impediment to flow. And no wonder the 109 is as famous as it is. But is it ideal? Think back to our original theoretical diagram, where what you really want is for the flow effort, the breathing effort to drop as soon as the valve opens, stay down in this 0.6 to 1 range. And to be honest with you, the 109 doesn't cut the mustard. Now, this was one reg, and there are, without a doubt, other castings, other moldings, other brazings of that case that will perform better. So I don't mean to indict the 109 on the basis of that one reg, because it's timeless. Conversely, if you're going to go cheap, as many divers do, it doesn't cost much. It hangs there in my golden triangle against the out-of-air diver that I'm never going to run into. And if I have to give it, well, we'll do it. It still works. And let's look at that same zone from 0 to 6 cubic feet a minute. It's still breathing Well, this is tuned very hot. This one was tuned to 1.4. Most of them are tuned to 1.7 to 2. But even in this range, it's still doing just fine. But what is the Venturi performance of this reg in high flow situations? It's a piece of shit. It meets Aqualung standard. Aqualung standard right there is 6 inches at 15 cubic feet a minute. And at 15 cubic feet a minute, this regulator topped out at 5.5 inches off the top of the graph there. But it met Aqualung specs. But compare that with the 109. Compare it with any other regulator on the chart. You don't want to be breathing this here. And I don't know of a technical diver that would wear one of these anyway at 150 feet. So it's a moot point. But the point is that Venturi mechanics matter. Was another aspect of this. When I ran this on the rotameter, you'll notice the rotameter was filling up full of water. This regulator was vibrating so vigorously, even stuck to the end of that rotameter, that the exhalation valve was fluttering. It was so much turbulence inside that case that that Venturi, little as it was, sucked water droplets into the rotameter. I had to flush this through. It was it was terrible. Well, I ran an atomic through the test apparatus about 2 regulators after this, and damn if I didn't start seeing those droplets of water coming up again. And I thought, oh my God, I, I guess water drained out of the top back into the tube. What's going on? This is an atomic. There's nothing wrong. So I cleaned it out. I disassembled it and hooked it back up again. And I fired up the atomic, and sure enough, it filled up with water, just like it shows there on the right-hand side of the picture. And I thought, this is not right. What didn't I do before I started this test that all of you should do as do-it-yourself equipment evaluators? I didn't suck on the reg without it attached to a tank. This regulator with its diaphragm on and a closed valve, I'm sorry, suck from the hose end, suck from the mouthpiece end. When I suck in on the mouthpiece end, I should not get any gas passed. It's a sealed system. Well, that atomic wasn't. And I took it apart. The water in there was not left over from the aqualung. It was because the diaphragm wasn't clamped in. This atomic came to me for sale, and it had been sitting in my pile of things to do. I just dragged it out for a quick test. It came in as a broken regulator. All it was the diaphragm not been clamped properly in between the faceplate, and so I got a $300 regulator for the $100 that I paid for it because it didn't work. Anyway, one reason for water to be there. But let's go back to our original setup. As I suggested to you, cleaning matters. And I ran into the same issue with the atomics that I did with that Apex that I talked about cleaning up. I had an atomic that should really do better. That when I got out to 12 to 15 cubic feet a minute, it was climbing up into the 2.5 inch range. I mean, not horrible, but not what I expect of a $400 second stage. Same issue. That the poor tuning inside it wasn't corrosion because of course it's a titanium barrel, but the trash inside the verdigris and the old seat, the old valve, had allowed a requirement for more spring tension and a little bit more turbulence inside the case. And I cleaned things up perfectly, and then I hot tuned it. I ran it to a 1.0 or 0.95 inches cracking effort. This guy did just fine. And in fact, it eventually even crossed over itself because I tuned it just a little too hot. When I got out to what is probably around 18 to 20 cubic feet a minute, I can't see it on my gauge because the scale doesn't go that high, but I could hear the whine on the suction, and it too crossed over, and that was kind of interesting. So cleaning and tuning is critical. If you're going to do a big dive, you need your regulators performing well. Otherwise, you're going to see a problem in an emergency out here at the edge of the spectrum with dense gas. Let's go back to the ordinary question. What reg do I buy? Do I trade in my toy for something new? Well, if you're like me, you started on either a D series, and we'll mess with the center balance poppets in maybe the next seminar, and a G250. Those were my 2 regs on my setup. And here it is. I mean, take a look at that graph. It does just what Pete Wolfinger said. It tunes light at around 1 inch, And as you start to run gas through that regulator, it sucks down. And properly adjusted, remember that Viva adjust that you don't go to dive versus pre-dive. You tune it so it terminates a free flow just shy of max. This regulator is as stable as can be all the way out to 12 cubic feet a minute. It only begins to climb a little bit after that. Maybe I could have tuned that just a hair, a couple of degrees hotter on the Viva vane and gotten even better performance, but that's the point at which it may cross over into free flow and blow at you. But there's your standby reg, big case, indestructible. The G250 has been around for 20 years, and there's performance that you just can't beat. What about the G260? G250 has that one problem. I can't get it any lighter than the spring will let me because it doesn't have a micro adjust. Well, if you look at the G260, early performance is exactly the same. In fact, it's even a little bit better at 4 cubic feet. It drops down even more quickly to half an inch of suck. And so this is my go-to deep water reg, I think, for now. Although we'll talk about atomic in just a moment. But as you can see, I don't know whether I've got a dirty reg or this is the 260 performance because this is just one sample. And you saw what I did with the apex and the atomic to improve that tail end of the graph. This one did start to climb at high end, but I will tell you that I haven't serviced that particular G260 in a year, so that may be spurious. In other words, you need to take this collection of lines with a little bit of a grain of salt out from 10 to 15 cubic feet. But if you have a reg that performs well that far out, you know you've got a sweet reg. And if you don't, you may have a problem reg, you may not. It may just be dirty. But there's your two classic barrel regs. But that's the big case style. What happens when we go to the small case style? We've already gone through this discussion. I guess I changed up the order of the cases. So let's move on to the small case diagrams. Here is our G260 as our modern example of the large case reg. And then in red, the first iteration of the small case variants, the S600. The S600 took ScubaPro by storm. Everybody loved the size of the reg. They loved how it breathed. But as shown by the improvement with the 620 and the changes in the case that you've already seen when they start molding the pathway for airflow, it doesn't do as well as it should. This is a strictly average regulator, and is the power of marketing over science. I have to say that it's okay, and it has the one value that ScubaPro brings to the plate every time. These regs are stable. They don't jump around like that Apex did, going up and then down and then either crossing over or getting more turbulent. This is a reliable, proven case design that has good flow, but the S600 was not as good as it could have been. And if I were going out on eBay to buy a used set of regs for a deal, I'd buy a 260 or 250 before I bought an S600. And the bling factor and the cost factor going to the 620 is not insubstantial. But look at that yellow line for the S620. Talk about stable. That reg is a rock. It does not change from zero to as far as I can drive it. And that's quality engineering. So there is the standard. It may not be Pete Wolfinger's ideal where things drop down to 0.4 and stay right there, but it's stable. Do you choose a 260 or do you choose a 620 Ti? By the numbers, I'll take the 260. But on the marketing side, I've lost that battle. The number of 260 adherents is significantly smaller than the people that like the small form factor of the 620, the lack of maintenance requirements because of the titanium barrel and that stable performance. Let's take it just a little bit further. There's that pile of gibberish all over the place. Where does it really matter? Well, if you look at this, it's the 620 form factor, we have a new boy on the market, and it is now unveiled. But here's the 270. What do we notice right away? Sorry.
That it's ugly?
Yes, it is ugly. Value has its own beauty, Poov. Value has its own beauty. All right. Once again, I need to clear the decks. Boy, I just need a larger work surface when I do these seals. All right, I'll just nudge this out of the way. Now, my shop owner loaned me his personal 620. Its pieces are all over the place, so I may be buying him a $500 regulator if I can't find all the parts, but we'll worry about that tomorrow. Here's the S270. Here is the 620 Ti. On the bottom, it looks pretty close. On the side, it looks, how do I do this? There we go. Still haven't got it right. It looks pretty close. On the inside, it's got that same cage. It's got that ultra tall diaphragm. On the inside, it looks pretty close. It doesn't have a titanium barrel, but then again, it's probably going to be about a $250 regulator instead of $585, I think. What's it missing? Well, it's missing a knob. This is a 620 Ti case. It's the same part number. Everything in this regulator is exactly the same as the S620 Ti at less than half the price. Lever, case form, Viva valve, exhaust valve, except it's got a plastic barrel. And we'll look at its performance graph in just a moment. You can guess at part of the issue right away. Here we've got this little thin titanium barrel because it's so strong it doesn't have to be very big for a given internal diameter to accommodate that S-wing poppet. Well, the same S-wing poppet is inside here, but plastic ain't as strong. This is fatter by far. So if you look at the outflow track is just about a millimeter narrower on the top side of this regulator. The outflow track for exhaust flow is about a millimeter smaller. And so you'd expect performance to be slightly less. Now we've got this knob issue. It brings us back to the whole micro adjust deal in the first place. Do you care? As a diver, I never touch the knob. I just don't. I tune the reg to what I want it to perform at. And if I want to avoid free flow when I do my giant stride, I turn it to pre-dive. And why is that an important thing? I mean, Aqualung has just introduced, is it the Elite? With a single control. There is no Venturi control specially. It's a single control. And they think that's a cat's meow because now Joe Blow, ordinary diver, just has to do one thing: on, off. What it does is it increases spring tension and changes the gate over the outflow port. Where is it here? It rotates that in. Actually, it slides it in at the same time. So when you turn this knob, it changes the gate and changes the spring tension. Well, you're conflating two different functions, and that's just stupid. I would never recommend an Aqualung Elite as opposed to the other one that's identical to it, but it has a separate Venturi control. Why is Venturi the thing to change when you jump in water? Because it doesn't change your cracking effort. When you're in a jam, you jump in the water and something's wrong. Panic sets in. Oh, I got to breathe. You start to have the last thing you want is to have to suck hard on your regulator. So with the Venturi detuned, it's just as easy to crack your reg open. It's just as easy to breathe at the low flows Where does the problem start? The problem starts out at that 16 cubic foot end of the curve, where you really need those high flow in the case, and you can't get it because of the turbulence from the Venturi. You don't need this at the surface. So this is the adjustment to make when you dive in the water. Dive and pre-dive. Don't mess with the cracking effort. So for my money, this is a huge value if it performs as well as the 620 Ti for $250 when it's sold by itself, and it isn't. It's sold as part of the Mark II as a set, or with the Mark 11, which is the way I bought this one. The work of breathing for this regulator is 0.57 joules, whatever that means. The point is, it's really low. The curve is really flat. It's easy to work. What is the work of breathing for the S620's Ti with the smaller barrel? 0.56 joules, 1/100th of a joule better. These are the same reg. This is $300 cheaper. This doesn't have a knob. This is kind of a slam dunk for me. And this just appeared on the market last month or so. I just got the first one that came into the shop because I just had to see what this was like inside. But everything else is the same. Just for grins, here's a little interesting side thing that Renee told us about at the last seminar when he introduced this to us. Here's something you've never seen before in your barrel. It's got a hole. It's got a damn hole in the barrel. And why is that there? Well, this regulator delivers so much gas, the valve opens so well, as does this one, that millimeter difference in outflow tract because of the fatter barrel actually makes a difference. Because there is 1 millimeter of impairment of going out the mouthpiece, this is more likely to develop Venturi-induced diaphragm suck. This puts out so much more, it puts out the same amount of air, but it's got this blocker in here in terms of the fatter barrel that prevents air from accumulating in the case and holding the diaphragm up. So it's easier for the diaphragm to collapse. They drilled that hole, or they added that hole in testing to blow the diaphragm back up to keep it from collapsing quite so easily. The Venturi-induced valve opening was too strong. So that was kind of a neat thing that you won't see in any other reg. And say it's just something for Regulator Geeks, but I think that was pretty cool. So let's look at the numbers. I don't know what the numbers are. I've seen the work of breathing curve once for about 20 seconds. They showed it. They said, don't take a screenshot of it. This is not for distribution. I'm showing this to you to show how cool we are at Scubapro. They didn't do a side-by-side with the S620. They just told us it was fractionally better and to take our word for it. So I can't share it with you because I don't have it. What I've got is instead this little poor man's comparison. This is at the surface. This isn't at 198 feet, but this is on my rotameter with two identical regs, but for the barrel. There's your 620 stable and flat in black, and the 270 is whisker harder to breathe, 1/10 or 2/10 of an inch harder to breathe, only out at the nether ends at high gas flow. Pretty awesome, pretty awesome. Now we're getting close to the ends, and I'm hoping somebody's going to jump in with questions soon. But I've got a couple of surprises in here beyond the surprise of the S620. Let me make sure I've got my act together here in terms of the next slide, so I don't surprise myself. Screw it. Let's just go to the next one and see what we get. We were going to talk about the competition, and I didn't really talk about them yet. Get my desk back here. Slides. And there it is. So I left the graph up there for you just as we look at it. Here is a $125 regulator. This one is made by Dive Gear Express or marketed by Dive Gear Express. The identical reg with a different faceplate is marketed by Deep Six as their bargain excursion regulator. They're both manufactured in the same factory and they share marketing rights. And it's El Cheapo. Who's looking for me? Somebody's calling, but I'll worry about it in half an hour. This is a $125 rig. We know how notoriously cheap divers are, and so it sells like hotcakes. Um, they've asked me to work on the service manual for it, so they sent me this for free, and so I stuck it on the machine. And as you can see on the right, the curve for the $125 rig up to 6 cubic feet is exactly the same as a $500 S620 Ti. When I saw that, my jaw dropped. It's not what I want, by the way. I want what the G250 does. I want one that drops down to 0.6 and stays low while I'm sucking on it, not one that comes back to my designed cracking effort. But this is the industry standard right now, and so I can't argue with it. So from 0 to 6 cubic feet a minute, you got this for $125, and you got the S620 Ti for $585. And when you look at this case, this is a little heavier in the water than the S620, but this will take some abuse and keep on cooking. Look how thick that case is. This is a workhorse regulator. So for a diver that don't want to spend much money and is going to not treat his gear very carefully, this is an amazing deal. Well, I sent that curve to Rene Dupre today, asking for Scubapro's input. He suggested to me that we may not get an answer out of the engineers. They may not choose to answer. But the question in my mind is, especially since this regulator looks to be better out at 12 cubic feet a minute than the S620 Ti, is what's wrong with my analysis? Well, the first thing that's wrong is this is a surface comparison. Nobody goes through 12 cubic feet a minute at the surface. And so how do we translate this surface question down to 198 feet or 160 feet, whatever, when air is thicker? The poor man's answer, my answer, is that I use 12 cubic feet a minute because that's the same at 6 cubic feet a minute at twice the density. It's the best I can come up with. But why is the inhalation resistance lower on this generic regulator? If you look inside, it doesn't have carefully molded shoulders, but clearly the Venturi performance of this regulator is superb. And so we'll see what kind of an answer we get out of it. I've posted this video to YouTube to see what kind of response I get from the few geeks that look at that stuff. But to me, it's a little alarming question. It's a very satisfying question that you can buy a regulator for $125 that at least to one measure will deliver air at no increased effort all the way as far as I can measure it. It does, though, make the whole business model for a behemoth like Scubapro a little harder to understand. And I'm hoping that the engineers are going to come back and say, Rob, that's all true, but the work of breathing loop for this regulator doesn't begin to compare. It's not 0.56 joules. That may look good, but the true work of breathing that you can't measure because you're doing a surface check is not as good as our regulator. And if that's true, then I will pull my video, pull this, and say, okay, I'm looking at the wrong measurements. But this is where Pete Wolfinger started us with regulator savvy. It's the poor man's equivalent to an Anstey loop, and I can't explain why this is so good. Let's take it one step further, or one last step further before we call it a day. And we'll look at another Scubapro's regs. that says engineering matters. This is the 350. This is not a balanced regulator. This is a downstream reg. And it too, for the first 6 cubic feet, looks identical to the S270. It's a small case regulator, just like the 620. So you'd expect some similarities there. But what's impressive to me is the high flow performance of this reg. Once you unseat that toilet seat valve, it's not a balanced valve, it's a wide open pathway. And remember, the C350 doesn't have that spring in the way. So when you need to deliver air in a bad way, this regulator just shines. The curve is starting to flatten out enough at 15 cubic feet that it may or may not cross over. I think you could detune that with a little tweak on the Venturi vane if you were down that deep and in that much of a jam. But once again, the 350 is a relatively inexpensive reg, and it may be why they used the 350 case for the 370 and why they went to a balanced mechanism. But this is where marketing comes into play now. They're not about to displace their flagship regulator and its successor by an off series, that C350 with that odd lever, no matter what the numbers say. And the numbers are very close. Talking about Nat Whisker way, but this kind of difference is significant. And I'm interested to see the work of breathing loop for the two if I ever get a chance to see, because there's a lot of mystery numbers in here. But this is pretty easy to look at and say, okay, that seems like a difference to me. If I'm flowing a lot of air through a regulator and it doesn't take much effort to breathe it in, that's good. If I have my Aqualung ABS and I'm having to move a lot of air through that regulator because I'm deep and I'm working hard, and it's 6 inches to pull a breath instead of 0.2, that's not as good. So if that difference holds, then that also means that the 350 is better in some circumstances than the S270. But you'll never get an answer out of Scubapro that'll talk about it because it's such a complex market. It's such a difficult business to make a living at that this is the kind of stuff for regulator geeks. That's all I got for you tonight. Questions, comments?
Rob, where would we start seeing 7 or 8 cubic feet a minute?
Well, as I suggested to you, if you were breathing hard, you at the surface for 0.3 of a second, you see 8 cubic feet every breath. If you were swimming for your life in a current off Cozumel and you wanted to get out of the waves and you went down to 5 feet, but you were still trapped in the current, you're just trying to get out of the wind and you're just swimming to make it to shore, you would see 8 cubic feet for 0.2 of a second with every breath. What would your reg do to you then? Would it get a little harder? I'm guessing in the panic, you wouldn't even notice, but it's true. What I don't know, what I try and pry out of Herman, our buddy on ScubaBoard, is that what's the equivalent at 30 feet, where you've got twice as many air molecules? Is that same 8 cubic feet a minute when you're hyperventilating and swimming for your life the equivalent to 16 cubic feet on my toy because there are twice as many air molecules? I don't know the answer to that, but I think it's heading in that direction. And that's why I look at performance out at the right-hand edge of these curves, recognizing that there's a lot of noise in there. There's the noise you saw tonight with the dirty regulator versus the clean regulator. There's the noise induced by a slight detuning versus a hot tune. And then there's the noise from design factors. The design factors are the manufacturer's issue. Everything else is a maintenance and tuning issue, which is why your local yokel at the shop is not the person to go to if you need max performance. But I think the answer, Kuv, is that moderate to heavy work at 30 feet and moderate work at 60 feet is the equivalent to 8 cubic feet a minute or more. So you want a reg that will perform well then. And right now, the old G250 is looking pretty sweet. The S270 isn't looking bad. But then, as you can see in this last graph, in the moderate range, in staying out of the technical diving range, they all work. That whole lineup works. My lack of enthusiasm for Apex persists here for this reason. It persists for other reasons with that first stage seat nonsense that's been discussed. It persists because, and I was going to do this for you tonight, if you look at the Apex purge button, it's a very short throw. And one of the things that I always do when I'm checking the tune of my regulators is I'll take it, I'm going to bang on that purge button or pull the mouthpiece off if I don't get a satisfactory answer, and make sure that that thing free flows. If I do a brisk bang, it should free flow because that's tuned right to the edge. And then, of course, I just stop it with my finger like I always do. You can't do that with an Apex regulator because the throw distance on their purge button is so small that it gives this half-hearted meh, meh, but it breathes just fine because the diaphragm moves much further than the purge button moves it. But I can't test that on the surface. Not another reason for me to be an Apex hater. Not that it's bad stuff, but just an aggravation. I like to be able to see what my reg is going to do before I climb in the water. I think you see 8 cubic feet on every deep dive if you work. Not if you dive like we did in Bonaire, just kind of lollygagging along. But if you have some current and you're at 60 feet, you're going to push that limit. But all of the good rigs now, even all the cheap rigs right now, are still just fine in that sweet spot. How do you choose what you want? Well, you like the purple faceplate, or you like the titanium, or you like the value. Pick a reason, but don't sweat your choice. They're all just fine. With
Okay,
one
thanks. Because
exception.
I was just trying to quantify it because when I put my regs on the rotometer, I see 6 cubic feet. That damn thing's blowing pretty hard.
It is. Yep. And you run up 16 cubic feet, your tank is just going fast. So the closest approximation I could think to that is depth. Is something happening for moderate work at 4 atmospheres. That's where it's equivalent to all this noise and tumult on the rotameter here on the surface. So, but it's not an entity machine. And Renee said I need to go down to Scuba Labs in Catalina and see if we can have a good reg, bad reg on this surface curve and compare their ANSTI loops and say, see, yeah, there's a correlation there. So if you can run a flow check on your rotameter, you can get a feel for what the ANSTI loop is going to look like. I don't know if that's true or not. I suspect it won't be as close as we want it to be, but I think there's a correlation. All right, guys. Well, I think it's the quietest group I've talked to in a while.
We're all in the middle of the week here,
Rob, I noticed the G500 had a second aspirator hole. Do you know what that was for? But it was on the other side, I think, not towards the membrane, not towards the diaphragm.
Second aspirator hole in the G500. Oh, this little deal here.
Yeah.
I don't know what that is for. That's a good question. Let's see. It's going to be facing in this direction. Levers on the bottom. That's going to be facing down. I suspect that I'm sorry, I haven't opened a G500 up in 10 years.
Is it a reversible regulator, Rob? Can you swap it from the left side to right side? No.
No, you can't, because the diaphragm lever would put the main breathing hole on the wrong side. No, I suspect there is. It may be something they drilled in for Venturi reasons, or it may have a little plastic piece that just happens to cover that up as you slide it in. Without having a 500 in my hand, since you just loaned me this barrel.
I haven't seen anything that slides over it, but
you haven't. Okay.
No.
Yeah.
But it's there, and I have no idea what it was.
Good question. I'll ask Renee next time I get him on.
Oh yeah, that would be cool to know.
To pin down, but I'll try and find out.
There was a great question further down in the chat about testing atomics. What do you do with the AFC feature? Do you push it into max, or how do you test those?
Yeah. Where's my atomic? Here it is. That is another a reason that I have some concerns about my testing. You'll see here's the T2X curve right out here. And if my suggestion that the atomic is, that the 14 cubic foot a minute is roughly equivalent to depth, then as you know, the atomic AFC is going to pull that vein back. This little vacuum in here, or this little surface atmospheric pressure, is going to get the vein pushed in. For those of you that are not familiar with atomic, put it on the overhead because it's actually an interesting mechanism.
Mhm.
And so to answer your question, the right way that I should have tested this reg is that I should have gotten another vein assembly, and I should have snipped off 3/8 of an inch off the vein, so it would
Oh.
look like it does when it's pulled back.
Actually,
Then I might have gotten an equivalent answer.
actually, if you unscrew the cover and you push it in the dive position, then you seal the cover again, it stays there. This is how I dive my primary. So mine
is okay.
Yeah, mine is always on max for my primary.
Very cool. I learned something every time oh, this is great, George. Thank you. That's a great example. So let me show you what he's suggesting. That's very smart. That's very smart. So what George has just suggested here, let me get rid of that stupid slide. We don't need that anymore. The AFC, or automatic flow control, lives here on this is a T2X. This is their Bling version, and the way this is interesting too. You can see that Pete Wolfinger was getting ready to quit ScubaPro when he wrote his book, because this mechanism is diagrammed in Regulator Savvy, but was never incorporated into a ScubaPro regulator. And you can see that by the time he left, or the other engineers left and formed Atomic, that they wanted to do some things like this that ScubaPro didn't bite. So what we've got inside an atomic regulator is the standard vein right there. So let me pull the faceplate off, create a little room where you can see, because we do have one more thing that we can chat about for as long as people are hanging around, and that's the seat saver in here. That's worth chatting about. But anyway, if I open this up so you can see through it now, there's the Viva vein, we'll call it that. And what happens is that when this compartment is covered up, it's covered up and it's got a pocket of air at 1 atmosphere. As you descend in the water column, water goes through a little crack in the case there, right alongside the valve. And since you have more ambient pressure than you have at 1 atmosphere here, this little vein, let's see if I can demonstrate it, slides in. When it slides in, nope, it didn't stay. In any case, the Viva vein, there it is. Viva vein sort of pulls out of the way. There's less blockage for airflow, and this rides much higher at 60 feet. This all happens automatically as you dive. When you hit 60 feet, it maxes out. What George has just told you is that he changes this so that it's not pressurized at the full atmosphere. It's fully withdrawn, so that he dives his regulators this way all the time. And that is a great way. I will run a test, and I will send you a picture
of the
atomic with the vein withdrawn, so we can see exactly what the difference is. That's very smart. You're a smart guy. Very good. I like it. That's certainly cheaper than cutting 3/8 of an inch off the end, and it also eliminates the factor that there's a little hole in there where it slides, so that would change the turbulence. That's very smart.
I only do this on my primary. My octo remains normal, because then it seals off, or it goes on minimum on the surface. But for my primary, I want it on full all the time.
Can you feel the difference at 15 feet?
Yeah, you can take a deep breath.
Subtle.
Yeah, you can take a quick deep breath, and you have the Venturi assist. Sometimes it just relaxes your lungs if you want to take a quick deep breath. It's kind of nice when you're decompressing.
I like it.
Yeah.
I like it.
Thanks.
I have not heard of that before, but that's a very smart workaround. I like that idea. You must have talked to other people about this. Or do you have people that
I might have mentioned it on ScubaBoard once or twice, but yeah, so far haven't had
take
the
some
chance to
pictures
talk
and
about it.
post a thread. That's a smart thing. Yeah, go ahead.
Yeah.
Take some pictures and post
Good
that.
idea.
You should take credit for that. That's a very smart move. I like it. I like it.
Thank you.
Since we've got the atomic open, it's worth talking briefly about the help me remember what's the size? Is it 1/8? It is 1/8. Yes, sir. So if we pull the barrel out of an atomic, it's fun to look at the orifice. This is not on the subject that we were talking about because it's a Regulator Geek issue, but we'll open this up. I'm just going to slide this out. And you can't get this out unless you disassemble the knob assembly here, but now it'll come out. And I'm going to pull the lever past vertical to get the little feet out of the way and drop the poppet out of the way. So now the mechanism is clear, and I can unscrew this orifice. Now, just like in the seminar, who can see my orifice adjuster on this outrageously cluttered bench now? May have to go get another one. Okay. So we'll unscrew the orifice all the way, and you'll get to see the magic that Atomic brings to the plate. Remember that Scubapro used to have a seat set saver using the balance chamber. Now remember that your orifice is the most delicate piece in your regulator. And so Wolfinger's manual mentions the fact that the orifice is a perfect fit for the brass spade. There is just no way I would ever stick a metal tool in there to dislodge the orifice. So if you're going to slide it in there, give this a nice gentle push. Here comes the mechanism. And you're going to see what makes Atomic in a league of its own. Here is the orifice for, okay, here's the orifice for Atomic. What did I do with the orifice for? I had the other one just nearby that I wanted to put under the microscope. Here is the orifice for the competition. The difference is that the threads for Atomic live in this little removable sleeve. Because there is nothing on the sleeve that has threads to engage it, that means that this orifice floats in the sleeve. So how does this ever seal to the knife edge? Well, the fact is it won't. And what they'll tell you, rinse your Atomic regs, you got to remember that the valve is open all the time and water will go up your hoses. Especially if you have your first stage lower than your second stage when you're rinsing it out, or if you throw them both in a tub of water, that's kind of a bad idea. I love Atomic, so the way I clean it is I just throw the first stage on the sink counter and throw the second stage in the water and just leave it overnight, come back and done. Because the valve is open. The only time this valve closes is when it pressurizes. Because now you've got 135 psi applied against this 1/4 inch or 1/4 inch plus diameter item. And because of the increased diameter of the outside, it pushes on the orifice and it jams it up against the knife edge and it seals. So the only time you can tune an Atomic is under pressure. So you need an inline adjuster so that you can tune it pressure. I mean, you can take it apart and rotate it and take it apart and rotate it the old-fashioned way. That it all works. But the point is that when you depressurize the regulator, there is a little tiny part sitting in there, and that's called their wave spring. And that little spring is a non-flat disc, and when it comes under pressure, it becomes flat. When it's depressurized, it reassumes its little curved shape, and it pushes the orifice back about 1/4 of a millimeter, which is just enough to take the pressure off of the seat. So that if you ever look at the poppet in an atomic regulator, oh, and I just happen to have one, there is no ring. An atomic poppet will last a decade. Now you still have to change it every 2 years because that's the requirement, or three years if it's just a T series. But the point is, there's no imprint on this poppet because the knife edge never sits jammed against it except when you're diving. And when you're diving, the balance mechanism keeps that pressure down to about 4 pounds. So these things last forever. And you compare that with the seat that I had out here. That was a new one. Oh, here's the seat from the. Oh, this is a new seat too. So it's not showing the ring, but it takes about 8 hours for an impression to form. If you leave a reg pressurized overnight, and you've already got a groove in the seat, that just doesn't happen with atomic, and it's pretty magical. But the haters say, well, I can never never wash my regs properly because the orifice is always backed away and the thing will leak. All it requires is a little change in technique. Just make sure your second stage is below because there's water going to get in the hose. And if you haven't got a tank to blow it out when you're done, just hang it from the towel ring in your bathroom with the second stage down. The water will drain out that same open valve and you're good to go. As long as it's fresh water, not quarry water, not salt water. But I think this is just the coolest thing since sliced bread because it makes the second stage last for years. You know, you can go 3, 4, 5, 7 years between services on a first stage, as long as the mechanism is sealed. Because if you're careful about keeping salt water out of your first stage orifice or where the tank hooks up, you don't let little droplets of salt water get in. Then the mechanism's dry. It's good. Those new Viton O-rings, not like Buna N, they'll last for forever. Buna only lasts 5 or 10 years. So first stages go for a long time, but not second stages. You know, they're just filled with salt water and stuff crusts up, and they really need regular service. And one of the primary failures is that low pressure seat. It gets its indentation and just seems to stiffen up. But Atomic has beat that. The only problem is that is so slippery that it's a little finicky about tuning. Retune it from time to time, which is just one more reason to become a do-it-yourselfer. So you don't have to go to the shop.
Yeah. About the reliability, I noticed, we chatted about this, that last time I was on the WKBP website, I noticed that some of their old school guys switched to atomics. And I thought that's a testament to the reliability. But I got a direct message and somebody said it in the forum. If you depressurize them and then the water gets in and you open them in, then some people have free flows. But I had no problems with them, so I like it.
No, there is an issue. I mean, you can't use it for a stage reg. If you're going to dive it as a stage bottle and you turn off your tank, and for some reason you get depressurized, then it's not just a little water up the hose; it's at ambient pressure pushing it all the way up to the first stage. Yeah. But a pistol will tolerate that too.
Yeah,
it's not like a diaphragm that locks up. So,
question I have though is, have you tried generic poppets or Scubapro poppets in the Atomic? Because the Atomic has proprietary poppets that are lined with metal under the silicone, right? So
yes,
I wonder.
I haven't tried it. But the dimension is the same. If I take a generic poppet, here's one from Piranha. I think this is one from Piranha, and I push that into the hole. It fits, and it's got a hole, and it seals, and the the height of the top. There's no reason it shouldn't do just as well. I'm not quite sure what the purpose of that metal insert is in the reg. What I am sure of, though, is that the composition of that silicone is so squishy that it's just really easy to tune it light, and I do love that part. This rubber is just wonderful stuff. So I'm pretty careful about sticking close to that. But that's a good comment, however, because if you look at, where'd the other one go? If you look at the S-wing poppet and the seat that Scubapro supplies, you do have a difference there. And I'm not sure of the significance of it, but if you compare a generic poppet or an atomic poppet with a Scubapro poppet, you will see that keep missing the transition button, sorry. You will see that the thickness of the two is markedly different. The Scubapro poppet is very thin, and I think that maybe resists forming as deep of an imprint as the generic poppet would. There's not as room for it to squish. But the tuning instructions for Scubapro are different from most other regs. They advise that you seal the orifice with a kiss to the seat and no more. And my habit has always been to seal it and then add 5 minutes on the clock, add 30 degrees of clockwise turn to put it in, just a 20th of a millimeter deeper, because of the inevitable imprint that's going to appear. If you just try and leave it at a kiss, you're more likely to have it free flow later. I'm not sure what the right answer is.
Rob, thanks for having this. I got to run. We'll see you guys some other night.
Goov, this is great. I think what we'll do for our next one is we'll respond to the guys that have been asking for a center balanced discussion. That's just a whole different ball of wax. Everything works differently with the D series and the Pilot. I've just been reluctant to do it just because there's so many parts in the Pilot that I'm a little. You can see the mess that I create in an evening, and I hate to think of Pilot valve parts on the floor, but I'll do it. And
sounds like a plan.
Fun. So
see you
we'll
guys.
do center balance next, and we'll do Poseidon after that. So that'll be the next 2 visits, unless somebody comes up with an idea. If you have an idea, send me a direct message on ScubaBoard, and we'll plan to talk about it. Thanks for joining me.
Thank you.
Thanks, Rob. Really appreciate that.
All right.
Good night.
That was brilliant.
I'll stick around for a few minutes afterwards if any of you have questions that you wanted to ask offline.
Robert, Bob Westfall.
Yes, sir.
Hey, so
Hey,
you ran the 350. Did you run a C370 at all by chance in comparison to what that conventional poppet does?
I haven't. I don't own a C370. I haven't been able to bring myself to buy one. It just irritates me that they took that beautiful downstream poppet that the 350 has with no spring in the way and then changed it to a traditional balanced rig. I don't know the answer. I talked to Renee today, and he mentioned the C370 in passing, and said that the worker breathing loop is almost as good as the S270. And so we're talking 500ths of a joule. Everything in Scubapro is now between 0.56 and 0.66 joules. That's kind of their standard. It's half of what the CE requirement is, so they know that they're never going to have any trouble. So I don't know the answer, and I certainly don't know what my course findings would be on my toy. But then I've got to find out from some engineer somewhere what the correlation is with dense air, like the Anstey loop uses, or is there any correlation? I'm sure the quick answer from Scubapro will be no, you're just doing the wrong thing. But I need to come up with some explanation for why the G250 and the C350 are down at 0.2, and the S620 Ti that costs $300 more is up at 1.2 inches cracking effort. I want an easier breath at 10 liters a minute. 10 cubic feet a minute. If I'm swimming for my life, I don't want to have to argue with my second stage. And that's the other thing that bothered me a little bit about atomic, and so now I'm really pleased about George's suggestion to pull that Venturi vane back a little bit, because unlike Scubapro's Venturi vane, where it's a flow deflector that improves Venturi, I get the feeling that the atomic vane is more a turbulence creator that they pull out of the way at depth, and so the less of it around, the better. And I'll deal, as George does, with the occasional puff of free flow just by cranking down on my. There might be a reason for the knob. There might be the reason for the knob in an atomic, that if you pull the Venturi out, you may have to detune your reg a little at depth, and
that's what I do. Then I detune it. Well, if it's in my mouth, I'll have it on max. But if I want to detune it, there's no other way than the knob.
Yep.
Yep.
There's very few divers that dick around with it like we like to, but I think it's fun to talk about.
Yep.
I think one of the most interesting things I learned tonight was that some regs are shipped in a rental configuration, and you can just flip them around for higher performance. I had no idea.
If send me a message, I will forward you the old. What manual is that from? I think it's from the G250 HP. It's also in some of the S manuals, the early S manuals, where they talked about what the smart tech can do to improve performance for the demanding customer. And
yeah, interesting. And it's also great seeing your enthusiasm. I think I picked up on your enthusiasm for the Deep 6 and or DGX line, and for such a value and for such support they have for the DIY community. I think it's great that their products seem to be solid.
I think they are. The bone I have to pick with the value line is that, at least on the diaphragm side, none of them have removable orifices, and that's what makes the Mark 17 or the Mark 19 or the Aqualung shine, or the Apex FSR over the more basic Apex, is that the body, the expensive heart of the regulator, doesn't contain the volcano. That's a slip out and replace phenomenon, because if you replace it, that's cheap. If you want to restore it, it's so easy to restore in your hand with some micro mesh, and working at the bottom of a 1-inch hole on a diaphragm regulator like the conch shelf or like Deep 6 and the rest is very difficult to do. But that's a minor quibble, because for $200, just get a new one. I'll just bend to the economics of it and say, yeah, get a new one. I was really tickled to see that flow diagram. And Derek at DGX wrote me back and said that they actually have ANSTI loops, not for the reg that I showed, but for their extra line. They have an ANSTI loop that they either supply with the reg or will share with the purchaser. So that's good to see. I'm going to have to get one and look at it and compare it with the big boys. That's a tough business fight, value and expense and bling and titanium versus performance.
Just performance, yeah.
Yeah. Now,
when
their chrome coatings. Say again?
When you were going to break out the DGX regulator, I thought you were going to break out the G260 Mark 25 knockoff.
It's not in here. It's out in the hall. People say that about the DGX piston, and it certainly has a Mark 25-ish shape, but it isn't. It really isn't. There are only certain things that you can do with a turreted piston, and if you put them side by side, the DGX reg is markedly shorter. It's made some interesting design changes, and we can talk about that. They take offense at being called a Mark 25 knockoff. They like to think that they've instituted some design ideas that are unique, we'll have to look at that sometime to compare the two. I'm a little afraid of going there because I have a good relationship with Scubapro and with DGX both, and I don't want to put them into a pissing contest with each other because they're at different price points, they're at different build qualities. I mean, you talk about the chrome and the cases for Scubapro. My God, it doesn't have to be as thick as an Excursion, and the Scubapro cases and their plastics just last forever. They're just superb build, superb engineering, but you do have to pay for it, and it's different strokes for different folks. But the fact that DGX and Deep Six can provide that sort of breathing performance in a rig, which may not last 30 years, at a price that's within the range of the average diver, that's magic. That's a good contribution, and I don't want to have to say which one is better. It's two different markets, and to the extent that performance matches, it only matches early. I think you've got to pay some price for value, and it probably has to do with longevity and finishes and chrome. But I'm impressed with what I see so far. I think if I had to pick one thing, it's a legacy of the Hog, which is what led to the Extra. The Extra second stage has an exhaust cover, which is very much like the Hog, and it's a good exhaust cover, but it's very thin. And if you break the tab that locks it in place, your Extra is toast until you get a new one. Disassembling the exhaust cover on the Extra reg is the only weak part I see, and that's a minor quibble. So
one thing that I came to appreciate since I moved to California and do the beach diving here, that the old S600 and the Atomic adjusters just are immune to any sand getting or silt getting into the threads. Everything else that I had.
Don't get me started on Aqualung regulators and their adjusters. Every Aqualung regulator in the world, you take the knob and you turn it and it goes. It's just exactly the dimension of a grain of sand. It's not wide enough to rinse out, and it's not tight enough to seal. It makes me crazy.
Yeah, I really like how the S620 and the G260 have the O-ring on the outside of the knob.
Yes.
From the outside, you don't get any sand in. But if you have it as an opto and sand gets inside, then it can still get in there. But not the S600 and the Atomics. It doesn't matter. If you have sand outside, inside, they're just immune.
Yeah, subtle things.
Yeah, and I thought, the plastic, I don't like it. I like the G250, but they actually thought about what they were doing. So it took me a couple of years to find that out.
All right, folks. Yeah. Well, this has been fun. It's a little late on the East Coast, and my phone's been ringing in the background. I'm sure it's my wife saying, "What the heck?" Because she's in Wisconsin right now on a business trip, so it's a little late for her. I'll touch bases with her. Thanks again.
Thanks, Rob. Thanks a lot. Brilliant.
Loved it.
Thank you. We'll do center balance next.
Terrific.
Adios.
So after all that discussion, what's the takeaway thought with regard to all those graphs and worker breathing, and whether or not a rig that is stable at 1 inch from 0 to 16 cubic feet a minute is better or worse than a G250 that drops down to 0.4 and holds there? Here's what I'm concluding. I think there are two pieces to it. If you put a rig in the water that you've dry tested with the curves that you saw, the preload of the valve is going to decrease cracking effort. That's how ScubaPro can make the claim of its S620 Ti that it's effortless breathing. It truly is. When you put that rig in the water with the diaphragm 1 inch lower than the top of the exhaust valve, and you take away 1 inch of cracking effort, you go from whatever you've set it at, 1.2, 1.3, down to that -1. In other words, it breathes at 0.2 inches as soon as you submerge, because the diaphragm is lower in the water. That's effortless breathing. That's the same thing that you see with a G250 at the beginning. It's cracking at 1.2, and it hasn't yet started that Venturi induced drop. Then that same preload, because the diaphragm remains lower in the water column than the top of the exhaust valve, unless you roll onto your back and are playing around looking up at the surface. In the standard diving position, that ambient pressure assist continues throughout the dive at any depth. Does it take away a whole inch? I'm not sure, and that's probably not something I'll be able to ever decipher from surface tests, and it'll wait for that test at 130 feet to get some sort of a subjective feel when you suck hard off a G250 and suck hard off of an S620 Ti, which one feels a little different during that heaviest breath. But one thing I think you can say is that ambient pressure assist on the valve opening also takes away some of the spring tension. It helps the valve open. And I think what that probably means is that the G250 and what I thought was that excellent gears or signature bargain reg that dropped down to 0.2 at 16 cubic feet is probably actually slipping over into free flow at very high gas flows at depth. As long as that's consistent, as long as it's dropped into that level and held it throughout a range of gas flows, that won't be a problem for you as you breathe. We are used to that when we dive right now. A reg that you take out of your mouth underwater without inverting it will free flow on you. So there must be positive pressure in the regulator case all the time in the standard diving position, and we don't mind. We don't mind a half an inch of positive pressure because we close our glottis. We don't even think twice about that little bit of blow. It's part of what makes a reg effortless to breathe, because as soon as we open our glottis, the air just wants to flow. So I don't think that's an issue unless you get to a reg which is in negative pressure in this flow, and then as soon as you breathe a little faster, it shifts into positive flow. Then I think what you're going to see is what feels more like a stutter. And the G250 doesn't do that. The C350 downstream doesn't do that. The gears regulator doesn't do that. They're all fairly consistent when they drop into those low cracking efforts on the surface, which probably turns out to be slightly positive at depth. In sum, I think that the S620 Ti has engineered it perfectly. It takes an inch to crack it. As soon as you go below the surface, it takes nothing to crack it, and it stays that way throughout. And that's superb engineering. If you're a technical diver in a situation where you might have to work hard, you may want something that does cross over and helps you with high gas density, with carbon dioxide loading, with a high respiratory effort. And that's something more like what the G250 gives, what the G260 gives, indeed what Poseidon gives, with that blow of breath that helps fill your lungs, that a lot of technical divers with dense air have come to appreciate. So it's different strokes for different folks, but the net of it all is that the flat curve of the S620 Ti means it's constant performance at just about any rate of breathing, and probably at most all the depths. And the number of times where you're going to need a kick over into positive flow assist is going to be limited to a small number of technical situations. And those kind of divers already have their prejudices about what regs feel the best for them. And there's no convincing based on numbers. It's all based on feel. So thanks for sticking it out as long as you did. If you've made it to this little postscript, it's been fun working on this. And as I say, when we take this down to 130 feet and try them out, I'll let you know the subjective results. Thanks again, and I appreciate your taking the time to listen.